Thanks for the introduction, Azalea. So glad to be here again. I'd love to show of hands actually. Who was here last year? Quite a few of you. Okay, welcome back. And who's new so I can see? Great. Okay, about half enough. That's great. Okay, so I'm not going to really assume any of the stuff that we looked at last year. This is sort of starting from the ground up. And the general topic that we're looking at today is something called algebraic effects. Actually, you sort of touched on some of this, or at least some of the idea of this in Joachim's talk, when he was dealing with the options, and there was an evaluator, and at some point you were trying to do division, and things were going wrong, and you needed to sort of rewrite the code to make that work out. So that sort of brings you into the territory of monads, and you saw things like do notation. And what this talk is about is a kind of a perspective on monads and on effects. So we would call things like the option type that you saw earlier an effect, and on some of the research advancements that we've been making in that general field. So I've kind of planned to have two halves to this talk. So the first half is going to be largely historical and motivational, so trying to understand the history of algebraic effects, to understand how we got to the position that we're in today. And really it's sort of completely non-technical, and it's a bit of a cartoon, but the idea is just to give you some motivation for why as programming languages people we're not interested in this problem at all. And then my hope is that the second part will be looking at a library that I've developed called the Effective Library, which I've released on GitHub, and I'll put a link later on, which you can download and have a look at. And the idea is that it has implemented some of these ideas, and we'll just have a play with it. So that's the goal for today. Oh, and my pointer's not working, so let's try this. Okay. All right, so this talk is a brief history of the evolution of effects. In general, it's a programming language a story, and monads will heavily feature. And effect handlers are, in some sense, the new kid on the block. People have started looking at them maybe 10 years ago as an alternative formulation of monads. So they're not, in some sense, different to monads. They are strictly weaker, actually, and they are all, in fact, monads, but they're just a different way of expressing monads, which is slightly nicer. And then I'll be talking very briefly about something called higher order effects, which is where algebraic effects find their limits, but where we can push them a bit harder than before. And there's a big caveat here, which is it's really hard to tell a history of anything because there's just so much history to talk about. So I'll do my best to be accurate, but I will surely make lots and lots of terrible mistakes. If you hear me making a historical mistake, please feel free to raise your hand and shout at me on the spot. I'm very happy for live feedback as you go. So my story of God.
Will you explain those pictures? I didn't quite get.
Those pictures, they'll come on later. Yeah, they'll come on. Yes, yeah. They're largely there for me to remind my. There's usually a pun in all of my pictures, and they're usually just my own personal enjoyment. So the story starts with the so-called functional imperative schism. I could ask the question that goes something like, who here is a functional programmer? And maybe like 3 people put their hands up sheepishly, and then who knows what imperative programming is? And everybody puts their hands up, right? That's usually how it goes, but none of you admitted to it just now. Good. So there's a schism between functional and imperative programming. You'll have heard of that. And it comes back to sort of 1933 or so, when you've got this chap Alonzo Church and his PhD student Alan Turing. And the pair of them had a different perspective on how computation works out, very fundamentally so. So Alonzo Church, the father of lambda calculus, which then becomes functional programming, and of course Turing thinking much more about machines with the Turing machine and assignment on a tape, and that's the perspective that he's beginning with. And interesting that they both sort of collaborated on this idea of computation right at the dawn of what we do. And so the story starts with programming languages, and so because we're talking about programming languages, I'll take you back to 1666, and it's the fire of London. So London is ablaze, everything is smoking and it's terrible. But it's not the only thing that happened in 1666. There was also some good news. Gottfried Leibniz finished his PhD thesis in 1666 on the art of combinatorics. And this is a really interesting read. It's an extended thesis about the proof of the existence of God from some hypothesis about various axes. And in particular, the thing that's interesting to us as programming languages people, is that he had in there like an alphabet of all human thought as his goal towards what he was trying to achieve. So his idea was that instead of like having an argument and then just going back and forth and trying to see what was true just by talking about stuff, why don't we write what we have as arguments down as symbolic things and then manipulate those symbols, and then we can sort of say, let's just calculate who's right and who's wrong. So his goal was to try and do philosophy in an analytical, calculational, symbolic way, rather than by just talking, right? And so that was his kind of big deal. And along in that sort of period, he's got this story about where he was trying to get from England to Holland, and he was detained for some time in the Thames by adverse winds. And during that time, knowing not what to do and having nobody in the ship except sailors, I meditated on things, and especially thought about my own design of a rational language. So he sort of starts ruminating on this idea of rationality and what we can do with that. For if we succeed, such as I imagine, we could reason about metaphysics and morality just like we do about geometry and analysis. So great insight, very, very long time ago. And it was a letter from Leibniz to Jean Gouin in 1677, so a bit after what we said. So was Leibniz the first programming language designer? So he's really thinking about syntax and tying that to semantics as a means of calculating, as a means of doing things like geometry analysis, but also a lot more than that. So maybe he's thinking about domain-specific languages already for that, the kind of stuff that we want to do today. Okay, so let me fast forward you quite some time to this talk by, I think, Émile Dubois-Reymond. So there is this thing called the Congress of German Scientists and Physicians, and that was kind of like one of the big conferences at the time where all the scientists would get together, and they would always have a keynote, and this guy was the keynote at that talk, and he finishes his talk with this quote, which is quite well known, where he says, "Ignoramus et ignoremibus," we do not know and we shall not know. And he's talking about the big questions of life. So how do things work? As in, what is thought, what is cognition? Like, science has no real access on doing anything interesting at all, and he's basically saying, we can't make any progress. We don't even really know how to do mathematics properly. What a complete mess and shambles. So what a nice way to end the day for everybody, right? Well, a few years later, there's this guy called David Hilbert at the same conference, also giving the keynote, responding to this quote with "Wir müssen wissen, wir werden wissen." We must know, we shall know. So he's sort of taken to defiance and saying, look, actually, I reckon we can start penning these things down. And so what he does, so David Hilbert was a mathematician, and he starts thinking about a whole bunch of different problems, so the Hilbert problems, where they articulate something like 100 mathematical problems that need solving. And they're asking themselves, if we could solve these problems, then we'll advance mathematics in a really interesting way. And so that's sort of where you get this nice coalition of Hilbert and Ackermann asking about the decision problem. I don't know how to pronounce this word. The Entscheidungsproblem, maybe. So the Entscheidungsproblem, the decision problem. So this is something that you might have learnt as undergraduates if you did computer science, which is basically the decision problem where we're asking ourselves, is it possible, given some input stream of symbols, to run that program and ask ourselves, will the program answer yes or no to some kind of decision problem? So the idea is that we encode some logical statements, we stick them through the machine, and the machine should tell you this thing is true or this thing is false, right? Seems like those are the only two possible outcomes, and so that's what they formalized. They said, look, wouldn't it be nice if, at least as mathematicians, we knew that there was a class of problems, in fact, the class of problems being like logical propositions, that we can give to a machine, and we can prove that the machine will either say yes or no. It would be good if logic was that way, right? And obviously, the answer is they were hoping for too much. So Gödel showed that in any reasonable system of logic, there will always be true statements in that logical system that can't be proven within that system. And I love the fact that Gödel was, I think, extremely paranoid and thought that something was wrong with pretty much everything. And he found this problem with logic itself. It's like there are things there that we know that are true that you can't encode in that logic itself. And the only thing you can do is make a slightly bigger logic to reason about that. But now what you've done is you've made a new logic with new axioms, and you need to reason about that logic as well. You know there are things that are true in that logic, and so now what you need to do is make a new logic, and so on and so on and so on. And it's like, and you can imagine this guy going crazy about this. So he basically shows there is no hope, we may as well give up. Logic is broken, it's the end of the game, let's go home. Great. Because, well, if it holds true, then perhaps there would have been an algorithm that could prove that one system was equal to another, right? That's kind of the thing that we could have had. We could have shown this thing is equal to that thing, and then we would know something about equality. And independently of this, we had Church and Turing saying, actually, there is no way that we could have an equality between statements. It's even worse than just not being able to have true statements all proven true in the system itself. It's that we can't even check that two things are equal within our logic. That's how terrible things are in general. So they wrote two different papers basically saying, okay, it is possible to have a language, a system, where you've got two statements, you want to check that they're equal, and we can't even say that, right? So what a pity, right? We're in real trouble now, mathematically speaking. Not only do we have we don't know whether we can answer yes or no, we can't even say what equality is. Like, this is really terrible. And the interesting thing is that both happens in 1936, and it happens independently. So I believe the story goes that Alonzo Church wrote his version and it got published, and basically scooped Turing just by a matter of a couple of months or something, and they didn't know about each other's work. And then Church looks at Turing's work and thinks, crikey, this guy's really good. I want him as a PhD student, and then hires him across from the UK into the States, and then they start working. I think, if I read between the lines, I think they didn't get along very well, and they kind of just, they knew about each other's work clearly, but they went down some very different lines. And so, I don't know if I've got slides about this. I forgot if I've got slides about this. So obviously the story ends up being that Turing's work goes down the line of Turing machines. You look at tapes, you look at these values going back and forth, and you're doing assignment to these things, whereas Alonzo Church is much more interested in the mathematics of assignment, or the mathematics of substitution. He's looking at the lambda calculus and how substitution is kind of the driving force behind things, and how all we need is something equivalent to functions. And so you've got this functional imperative divide happening right at the beginning. Okay. The history of programming languages starts something like that. But of course, programming languages without a computer are pretty useless. It's very nice that Ada Lovelace was able to program some stuff with Babbage, but it didn't really actually execute anything, and so it's difficult to use those machines. I should remind myself that when I'm writing research papers that are very theoretical. In 1945, we begin to see the dawn of computers as we know them today. It's World War II, you all know the story, I'm sure. The British are trying to crack the German Enigma. They need a way of being able to decipher those messages, and they realize that they need a lot more compute power, a lot more computers than they actually have available to them. Because in those days, a computer was actually the name for a human being who would compute the results on paper and pen, right? The interesting thing is that they obviously did crack the Enigma, and I don't know if this is true, can somebody correct me? I heard that after the war, the Enigma was obviously cracked by the British and the Americans, but they didn't tell anybody, and in particular, they didn't tell the Russians. And in particular, the Russians were sold all the old Enigma machines by the British on the pretense that, well, here's an uncrackable machine. If you want to be able to decipher all your messages, use these things, they're wonderful. And so the Russians buy a whole bunch of these things, and the British carried on. I don't know if that's true. I would love to have someone tell me if that's true or not, but I've heard that all the time. It's a good story. Anyway, back to von Neumann. So obviously he's thinking about how to execute computers, and it goes down much more Turing's line than it does the lambda calculus way. And so we end up having one of these machines. Actually, there's debate about whether or not the first computer was American or British, yada yada. I don't know how to resolve that problem. If we fast forward just a decade or so, we get to the first languages that are recognizably like the ones that we would see today. So Fortran would be the first in this genre, I would say, where we're looking a little less at machine code, so where you're just writing in binary, and a little more at statements, imperative statements nonetheless, because we're driving an imperative machine. And so here we have an actual, so this is what an actual punch card looks like. And so what you have here is 80 holes, or 80 characters long, and each one of these is a single byte, I think, or something along those lines. Sorry, it's 80 characters. No, it's 80 characters because it corresponds to the actual 80 characters that we have on our Vim terminal still, 80 characters wide. And then here you've got 0, 1, 2, 3, 4, 5, 6, 7, 8, which are the bits that you want to punch in. So along each one, so basically this whole piece of tape corresponds to one 80 long line character, one line of 80 characters, and each of these holes corresponds to basically the ASCII that you want to be punching in to that. So the code looks like this. You've got things like rewind, so you're still playing with tapes. You have things like loops, you have assignment of variables, and so on and so on and so on. Okay, so why are we here? Well, John Backus says, well, most of my work has come from being lazy. I didn't like writing programs, and so when I was working on the IBM 701, writing programs for computing missile trajectories, I started to work on a programming system to make it easy to write programs. So most people think that Fortran's main contribution was to enable the programmer to write programs in algebraic formulas instead of machine language, but it isn't, he says. What Fortran did primarily was to mechanize the organization of loops. Why am I pointing this out? So we think of Fortran, the formula translation language, as being very good at doing the kind of stuff where we have these kinds of statements going on up here, where you can start thinking about equations a bit more clearly, but actually it was the control of loops that was the thing that was interesting to John. And to me that's interesting because it was the control of an effect, the effect of looping, that was to him the insight, not the actual boring algebra of computing that was the point. Okay, if we fast forward just a couple years, we see a different language, completely different language, by another John McCarthy, called Lisp. So Lisp you can think of as being the first functional programming language, where McCarthy was thinking of doing things like Church's lambda calculus. So he was starting from the basics. Can we do substitution in the language? And so he ended up having this. And so you can see that, I should use this thing. You can see that he is very much thinking about having lambda functions right from the beginning. This is the first paper that he wrote on the issue, and he's writing lambdas right there. So he's taking a completely different view. This language has conditionals, it has recursive functions, and it has list processing in the form of what we call car, CUDA, and cons. So these very strange names actually corresponds to the address and the something, I've forgotten what they are. They're basically instructions in the previous machine that we were looking at. And what they correspond to are the head and the tail of a list, because they correspond to every bit in memory having a pointer to the current instruction and a pointer to the next one, and they were called the car and the CUDA pointers or something like that. And that becomes where we extract the head or the tail of a list early on. And what's interesting is that even like the 1960s, we're seeing conditional expressions being turned into things that look much more like pattern matching than the McCarthy if then else is actually a pattern match. We also see here, it's very hard to see it, so it's really small, sorry. We're seeing a map list function. So the mapping function, which, I'm actually maybe speaking to wrong people. Who knows about functional programming and the mapping function? Is that something that most of you are aware of? I hope so. It's a big deal in the functional world that you can map over a list. You have a list of stuff, you have a function, and you want to go over that list, changing all the values with that function. So these ideas come back right since the beginning. Here we go. So car and CUDA correspond to the address part and the decrement part of an instruction of a memory cell, and so those are the names that stuck. Weird. It's also the time when the word abstract syntax is first coined in '62. So in a particular paper, John McCarthy decides that that's a good way of talking about that. So what we've looked at are sort of the two precursors to languages of today. So we've had Fortran and Lisp, and Algol is seen as kind of like the first modern programming language with all sorts of features that we really recognize today, all put into one place. So you've got procedure blocks, named procedure blocks, and you've got things like recursion built in. So both iteration and recursion are there. You've got assignment and equality as distinct things, and you've got coding blocks, lexical scope, nested procedures. They invented BNF, which you will have studied when you're doing grammars. That was invented in order to specify how this programming language works. And they also distinguished between call by name and call by value. So they did a lot of work to put this thing together. And in fact, Tony Hoare wrote about this in '74 and said it was a language that was so far ahead of its time that it was not only an improvement on its predecessors, but on nearly all its successors. And there's some truth in that when we see the proliferation of programming language today, where lots and lots of languages get invented, and not always with any particular theory or idea in mind. It's just somebody knows how to write programming languages, but just does so because they want to, rather than because they have an idea that they want to express. Not all programming languages are like that, lots are very well designed, but there was a real gold standard set in Algol design. Okay, so Algol was a very imperative programming language, and Peter Landon knew this. So in 1964, he was asking himself, how can we understand the semantics of Algol, and what can we do about that in terms of what Church has taught us? And so he decides to start looking at how we can mechanically evaluate expressions and how that can be given a formal semantics using the lambda calculus. And so we have here on the left-hand side a block of code in Algol, and on the right-hand side we have what he calls the applicative expressions. And you can see featured there, it's got things like lambdas, which bind some variable names, and then we have a bunch of substitutions, and he's basically showing a translation between these two things. And so here we have a really early view on denotational semantics, where if you do any programming languages theory, what we tend to do when we try to understand what a language does is we actually try to understand what it is in terms of some operational, in some denotational model that we do understand. And so what he's doing here is he's saying, well, there's a program and what it does is this bunch of statements, but what it means is this equivalence with some lambda expressions, and we understand lambda expressions quite well because that corresponds then to the work of Church. So he also introduces something called the SECD machine, which is the first abstract machine for evaluating lambda expressions. So if you have a lambda calculus and you want to execute it, well, you need some way of sort of reifying that into a machine, and the SECD machine is something that we base a lot of our machines on today. So if you ever have a course on building compilers, it will be one of the bases you would use for working out through functional languages. And in '65, he actually shows the correspondence between Algol and the imperative applicative expressions, where I think he adds an extra assignment statement, and then he just shows that there's a nice correspondence between these. So this is the first time when we really have denotational semantics between things. A little bit later, in '66, he invents this language called ISWIN, which means if you see what I mean, ISWIN. And the idea with ISWIN, it was a language that didn't really have very many implementations at the time. I think it probably didn't have an implementation at the time. It was the language that was used in this very famous paper called The Next 700 Programming Languages. And the idea behind this paper, it's worth reading actually, even as a PhD student, because in those days, writing papers wasn't like it is today in many ways. There wasn't nearly as much mathematics, at least not in this paper, and it's very descriptive of ideas rather than actually showing you how those things are implemented. And you really have to read between the lines to understand what he's getting at. Actually, his language is, I find, quite difficult to understand, but it's still quite worth reading and thinking, okay, has research changed since those days? And it really has. But it's a really wonderful paper because what he says is that rather than having everybody invent their own programming language, wouldn't it be nice if we had a programming language that allowed us to define more programming languages? So a language of languages, basically. And so every time that a programmer wants to have a new domain to interact with the network or interact with some files or do some kind of new domain-specific thing, well, you have the language that defines those operations, gives the semantics of those operations, and then builds those into the language itself and allows you to continue. So that is the kind of the big idea that he is introducing it here. And prior to this, really, nobody conceived of languages in that way. It was always a single language for a single purpose, rather than one that has libraries that you pull in and you can do things with. Now, obviously, today, we always use and pull in libraries when we're working with large code bases, but this was, I think, the first time when that idea was put to fruition. Prior to this, languages were more sort of a language together with all of its interactions with the rest of the world, and now you can think of this as being bolted in. So, he also called this paper Church Without Lambda, because secretly behind the scenes, even though he was writing a programming language, he was just thinking, we're doing lambda calculus. It's a language that massively influenced Haskell. It had pattern matching, it had where clauses. he wanted it to have garbage collection, and it was indentation-sensitive language. Whether that's important or not, I'm not sure. But here are some of the, here's a fragment of it. So you can see you've got an expression, and you've got a where statement, and you can see and some more stuff to the where, and then he's showing how that translates across to the calculus. So he's sort of, if you're a Haskeller, this is almost Haskell verbatim, except that we wouldn't use the word and. That's the only thing that's different. Peter Noir, who's of Bacchus Noir formalism, so BNF, he's the N in that. He said, regarding indentation, in many ways I am in sympathy with this, but you would regret it because of the kind of rearrangement of manuscripts done in printing. So it's, I think it's a charming remark because A, people still find indentation-sensitive languages to be quite a weird thing. B, it's interesting that he's remarking this about manuscripts and how we're writing stuff. So obviously they were writing papers at the time, and typesetting was just as difficult then as it is today. So some problems still haven't been resolved. But another thing that's cool about reading this particular paper is that that's where you'll find this remark, because in those days, when you published a paper, as part of the appendix, there would be a transcription of the conversation that happened in the conference when it was presented. And so you can see all the big names having a little chat about what this person has just presented in the next 700 programming languages. So definitely recommend that reading, it's good fun. And wouldn't it be nice if we had those sorts of things today? Well, we don't, but we've got YouTube instead. Anyway, the big thing that was interesting about this particular language, though, was that it was equipped with equivalences for reasoning. So it's not just that you have a language where you have syntax and you can write some stuff. It's also that you can talk about terms and the equalities between those terms. So I think you probably saw some of that stuff in Lean today, where we're thinking about equality between things as an important construct. And that goes way back to Iceland in many ways. He was thinking about not just having a programming language sort of devoid of meaning, but how do those equalities affect the actual language itself? And so he had this idea that you should have equalities between sub-expressions. So if L is equal to L prime, then L of n equals to L prime of n, and you can see that here we have like the consequence rules coming out that we would be using in theorem provers. And so that was kind of built into the system. Then he also wanted to have an equivalence between different definitional styles. So he, in particular, wanted there to be a way to introduce variables using what we call let bindings, and also using things called where bindings. So from the ground up, he wanted this language to be very flexible, to allow you to state the same things in multiple ways. And what better way to say that these are the same by using an equality. So he's building equality into the syntax, into the semantics of the language from the get-go. And again, as a Haskeller, I find it really fun to see that the let-where division started way back when, even at the very beginning. In Haskell today, you can still write things in terms of let or where, it's at your discretion. Some people prefer one, some people prefer the other, and the more seasoned veteran uses a bit of both depending on the situation. He also wanted there to be equality between built-in expressions, so that's not too surprising. He was giving a semantics to things like, so this is like pattern matching on true or false branches of things. So if true, then do M. If false, then do N. And so we can see pattern matching playing in, but we can also see that he's thinking about the semantics in terms of equalities. And of course, he wanted equalities to be built into user-definable domain-specific languages, which he talks about in a paragraph. And this is what I meant by the charm of this work, where it's not so much like a whole bunch of equations and he builds up the syntax. It's more like he describes, problem orientation of isom can be characterized by additional axioms. In the simplest case, such an axiom is an isom definition, yada yada, right? So they talk about things rather than defining things like as we do today. Okay, so that kind of sort of starts to set the scene about a kind of a functional basis for programming. And I haven't talked too much about effect, but we'll get there. So iSwim was useful because it was good for reasoning and structured programming. So what is structured programming? Well, actually, again, we saw some of that this morning, where we were doing case analysis on the different constructs that we had in an expression, and the eval function was going by induction over the different terms. That's very much a structure based on the structure of the data that you're consuming. So the expression is a tree, and therefore the program that we write goes over that tree and uses induction. And that was explored quite thoroughly in around '68 by Burstel, and he started thinking about things like fold R and concat, which we call today, which are basically generalized programs for recursing through things. And he talked about having a function for sorting via tree flattening. So he's very much thinking about the structure of data and the orderedness of that data giving rise to algorithms as well. So that's where a lot of our view on how to program comes from these ideas. And we take it for granted when we're taught these things as undergraduates that it completely makes sense that we would use the structured data to structure our programs. But that's not something that was obvious back in those days. People just sorted things differently. I mean, there was a time when quicksort wasn't invented, right? And that was these days. And then the other thing is that he not only actually gave this program, but critically, he gave a proof of its correctness by induction as well. And so again, if you're doing theorem proving, you're always writing a program, and the proof of that program is often done by induction over the structure of the type of that thing, following the structure of the program. And I see the theorem provers here nodding because it's exactly what you do. You follow this pattern. So it's nice to see that even though they didn't have theorem provers, they understood the techniques back in those days. Okay, and then the idea was kind of really important. It took off. It made what was then a popular book, Structured Programming in '72 by Dijkstra, Hoare, and Dahl. And they said that there are certain close analogies between the methods used for structuring data and the methods for structuring a program which processes that data. So again, it's an idea that we should take to heart. I see it forgotten when people start hacking around in whatever strange language they're using, and you're just sort of writing an algorithm, doing the thing however you want it to be. But again, if we structure ideas, things work out much better. And I want to just return to the idea of denotation. So what is denotational semantics? And I think that this 700 programming languages paper is one of the first places where that idea comes out at all. So he says, the thing an expression denotes, or its value, depends only on the values of its sub-expressions, not on other properties of them. So he's saying what the meaning of a term is some combination of the meaning of its subterms. And that's one of the big ideas that we see in the work of Scott and Strachey in '71, several years later, where they introduce towards a mathematical semantics program of computer languages, which is the classic citation for denotational programming, or denotational semantics, sorry, where what they say is that, do I highlight this thing? Let me just go back. That the value of v0 plus v1, that's this big V on the outside, is equal to the value of v0 plus the value of v1. So those strange brackets, sometimes they're called Oxford brackets, sometimes they're called Scott brackets or Strachey brackets, were introduced in this paper where basically we say the meaning of this thing on the inside is the meaning of these constituent parts. And so you're building into this mathematical notation this idea that there is a syntactic language on the inside and there is a semantic language on the outer side of this thing. So where the syntax here on the inside is really just the symbolic stuff, the stuff that the trees are made of, on the outside of these brackets is the world of mathematics where addition is actually taking place. And this is really fundamental to the way that we do interpreters, that we write compilers today. We're thinking of the semantics of syntax by showing how you transform that and walking down the tree using exactly these techniques. Okay, so we talked about sort of this divide between functional and imperative styles. And I think that what Landon would have said about this is that actually we shouldn't be thinking about this as a divide, but so much as a kind of, there should be a synergy between them. So he says that Eystrom brings into sharp relief some of the distinctions the author thinks are intended by such adjectives as procedural, non-procedural, algorithmic, heuristic, imperative, declarative, functional, descriptive. Here's a suggested classification in the new word. He wants us to think about what denotative programming is. So what is the point that I'm trying to make here? I think it's wrong when we start putting ourselves into imperative versus functional camps, because that tells us something about the underlying machinery that we're looking at. The reason that we often do it, though, is because we're thinking about what the semantics are to programming languages that we're looking at. And I think we all agree that a denotational semantics is a good one, because it sort of points to what something actually is. But even in that statement that I've made, it's still controversial, because we have operational semantics as a completely different way of doing things, but they're not so incompatible. But he wants us to think about denotative programming from the ground up, this idea that you write programs, you have equations between those programs, and that's the driving force behind what you have. So Yeah, okay, so the point is that there should be some synergy. Okay, so where or how would we talk about that synergy today? Well, we use these things called monads. Now, I'd love to do a hands up. So who has heard the term monad before today? Okay, and there are a few people who haven't. Who could define what a monad is quite accurately? Right, and then the number goes down. And that's quite normal, right? So we've heard this scary word, and we don't really know what it means. And actually, that's quite typical. So monads, maybe 10 years ago or so, there was this time when people were writing lots of monad tutorials on lots of blogs and Reddit things. I don't know if that persists to this day. It might do. My good friend Brent Yorgi wrote this blog post about abstraction, intuition, and the monad tutorial fallacy, where he said, you know, in the end, everybody ends up writing some kind of article about monads when they finally understood them, and they use some kind of analogy. And so the analogy is, he says that monads are like burritos. Actually, he doesn't say that. He says, here's an example of the kind of banality that people come up with when they finally understand monads. They're just burritos. Actually, I think it's quite fun that we all come up with our own metaphors for monads. They're like burritos because they contain things, right? The food is on the inside and they're very yummy. The other words that people have proposed for monads are warm, fuzzy things, right? Because there's really nothing scary about them. But they have a scary name. So I want to just take us way back in history now to 71,000 BC. And the reason that I'm doing this is because in 71,000 BC, this rock came up. So this is like no joke. This is an actual rock in some archaeology museum. And the thing that's interesting about this rock, you can't see it too well on these screens, is that it has these red lines, these red ochre lines on it. And as far as we can tell, these are the first human inscriptions that we can find, that we know of, right? So there might be early ones in this out there, of course, but this is the earliest human markings that we can see. And so, you know, the right people have done that careful analysis on this. So it was from a 73,000-year-old cave in South Africa. And they've done some very careful analysis of the actual inscriptions to see what's there. And I think if you look very closely at what they've done, you can see that mankind has been striving for Haskell for a very long time. You certainly have the lambdas in there, but the Haskell logo is certainly part of it. Okay, maybe not so long ago, not in South Africa, 71,000 BC, you had these guys here who made the Haskell programming language. You can tell I'm more Haskell-centric because I keep on having references to the language. But they wrote an interesting paper about monads and I/O being central to the design of that language, and it's the first language that uses monads at all. So what are monads? They're basically a way of understanding serial computation. I say serial if I'm being careful. Most people will understand sequential computation as being the right notion. There's a slight distinction between the two, and serial is more accurate, but sequential gets the point across more easily. I see Azalea asking what's the difference. So the difference is a sequential computation goes something like, if you have P semicolon Q, then all of P needs to be evaluated before any of Q can start. That's sequential composition. Serial computation tells you that there's a data dependency between P and Q, namely that Q depends on the result of P. But it does not tell you that you can't execute Q at first. So you can imagine a world where you're doing parallel computation, and there is some of Q that you can pre-compute before you have all of the data in P. Well, that's a serial dependency rather than a sequential dependency. So if it's purely sequential, you can't even begin to do Q until Q is finished. But if it's serial, you can sort of pre-compute some of Q before you compute it. So that's the distinction between the two. Thanks for asking. Monads, okay. In part 2 of this talk, because I don't quite know what my timing is, I'm kind of just rambling at the moment. Okay, yeah. So what I'm hoping to do, it will just depend, I will just ask you questions later. Maybe we'll do a monad tutorial so we can actually get beyond the warm fuzzy thing stage and we can come up with our own analogies. That might be fun. Or maybe we'll look at the library. It's going to be a pick your own adventure later, okay? But I wanted to get into the history of monads before we talk about them. So they are a mathematical idea written about in MacLean's book. What does he say? The recognition of the power and simplicity of the use of monads and comonads came quite slowly. Sorry. They started from their use in homological algebra by MacLean, who mentioned them in passing, and yada, 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 right? So what's interesting is, so I've dug up the paper that has the mentioned in passing. So this is the paper. It's in French. Thankfully, I can understand French. I read the paper, and I don't understand a word. But the part of it that is in particular is something called bar construction, and the bar construction is uses monads as part of that. And it's just a tool, and it's not an idea that's interesting or important in itself in this, and it just sort of arises in this work. So Roger Goldman looks at the idea in '58, and he decides in one of the appendices that he needs to have, again, it's all in French, he needs to look at this thing more carefully, and he starts looking at things like continuations K and P is something that we call the join, which are now what we would really understand as monadic operations. What we have here in that paper are what we call the monad laws. So one of the things that we'll learn about monads is that something is only properly a monad if it has a couple operations and if it obeys a couple laws. Now, I'm picking this up. They're actually quite a simple idea to understand. We're just saying that, so think about what it means for something to be sequential, right? It means that if three things happen, P, Q, then R, it doesn't matter if P and Q happens followed by R, or if P happens followed by Q and R. There's a kind of associativity that's going on there, and that's what this law is describing. So that's all that monads are. They're just an abstraction of that idea of sequential composition. And for years, the mathematicians didn't give these things a name, right? They were just called the fundamental construction. And so, or just even worse, they were called triples, because a monad consists of three things. Some data, which they often call T, an operation which we would call return, an operation which we would call bind. And so they were called triples, or even just the letter T when they were used in mathematical parlance. So for ages, they were unnamed. So where did the word monad come from? It took a while to dig this up. They were first written by a guy called Jean Benabou in '67, and he decides that they're a play on the word monoid, because a monoid is a mathematical abstraction that has associativity built into it. And so monads are a kind of monoid, and so you get that joke about monads are just monoids in the category of endofunctors. Never mind. If you understand that category theory, fine, but if you don't worry, it's just jargon that category theorists like to throw about to make people scared. They're not scary. Other words are, so he says, yeah, okay, so our choice of monad comes from this example, and it's an example of monads. And also polyads are another thing together that he wants to talk about. Okay, whatever. I started touching and talking a bit about category theory. So many of you will have heard that category theory is this thing that some people in computer science do from time to time. We don't admit to it, but we do category theory sometimes. And so what is category theory? Well, it's been in computer science for a lot longer than you think. So category theory was explored quite early on by IBM, in IBM by Eilenberg and Wright. And they started using category for talking about what we call universal algebra. And that's quite fun because it's hitting really close to home, because what we'll eventually talk about, algebraic effects, the idea that you can talk about effectful systems in an algebraic way is a form of universal algebra. So it's kind of been the issue for a long, long time. And so they talk about the basic language being the theory of categories, and they are basically in some sense the precursor or the fundamental part of lambda calculus in some way. We also see Albert writing in '71 about using automata theory, using Levin theories as well. I don't think I've got too much to say about that. Another big sort of increase of category theory in CS came in 1970, when MacLean, the father of category theory, speaks to Gauguin and a few other people, and they formed something called the ADJ group, or the AD group, which they wanted to sort of rewrite the foundations of computer science using category theory as its foundation, very much like Nicolas, who's that French mathematician who's not a single person, right? So Bourbaki is the story goes, is a pen name for a collection of French writers who did rewrote a lot of mathematics at that time into a coherent foundational principle that we use a lot of that today. And so they wanted to rewrite a lot of the foundations as well. So they formed this group, ADJ, short for adjunction, because an adjunction is a fundamental categorical construction. And so they write a series of papers. In fact, this one is said it's called A Junction Between Computer Science and Category Theory. Ha ha ha. So terrible puns are also something that feature. I said they're a sign of they're a sign of great success. The project became hugely successful and influential. So lots of people picked up on the idea, and there was this paper about initial algebra semantics and continuous algebras. So initial algebra semantics, when Joachim earlier on talked about inductive data types are initial algebras. That's what it means to be an inductive data type. So they are, like, mathematically, that's where this comes from, actually. So they called this part 1, and then I think they never really made it past part 2. So I think they had something like 5 parts planned, but it never went anywhere. And then back in '75, you can see Burstborn Thatcher using monads to explain statement programming, but it's kind of more in passing and more semantic than what we would expect today. And you can see here that there are monad laws being explained. Oh, actually, I should actually point that out more carefully. They're talking about monads, and here you can see the infamous semicolon appearing between 2 computations. So we're thinking monads in terms of sequential compositions way back there. Okay. It's also interesting thinking about monads and the lambda calculus and what the connections there are. So Dana Scott, who was the father of denotational semantics and many other things, started talking about relating theories of the lambda calculus, and he thinks of pure theory. He thinks that the pure theory of functions is category theory. So he says everyone agrees that the lambda calculus is a theory of functions, but we must ask what kind of theory, and also have we got the best theory? Personally, I think we should also inquire how does it relate to other theories. Certainly, I find many discussions far too silent on this last issue. We're probably seeking, what we're probably seeking is a pure review of functions, a theory of functions in themselves, not a theory of functions derived from sets. What then is a pure theory of functions? Answer, category theory. So why are functional programmers so obsessed with category theory? Because functional programmers are obsessed with functions, and the understanding of the foundations of functions is category theory. So that's kind of where it goes. All right. So now we're getting very close to monads as we understand them today in all sorts of programming languages. In 1980, Eugenio Moggi thinks about monads and starts thinking about denotational semantics, or the semantics of computations themselves, and writes this fantastic paper, Computational Lambda Calculus and Monads. It's the first paper of this topic. It's again, the style is very different to the next 700 programming languages paper, but I would say another fantastic read. And here we start to see the real influence of mathematics in computer science. So this would be much more like a paper we read today in its style and function. And I would say it's really worthwhile looking at. So he says we take category theory as a general theory of functions and develop on top of it categorical semantics of computations based on monads. And he has things like side effects playing into this, side effects and state, that is, and we've got exceptions as an example right in the beginning. And he's thinking about this not as a programming language feature, but rather as a tool that we would use to reason about programming language semantics. And that's an interesting distinction because at that time, I don't think it doesn't look to me in Eugenio's work, he's thinking about monads as a programming concept. So it's not that we're going to program with monads, it's more like monads are a mathematical tool that we're going to understand programming languages with, right? And that's an interesting distinction. So the idea of, but then he does write this notions of computations and monads, and he writes about how there are different forms of computation and how monads give us semantics to all of those things. Again, it's a good read. But for us as programmers, the idea of using do notation, the idea of using monads in our programming came a little bit later. And I think you saw that this morning, had the do notation. Where did that idea come from? So the idea of programming in that style, I think, starts possibly with Wadler in '85. He's thinking about how we can replace a failure with a list of successes. But he's not using monads directly at that time. So he's thinking about exception handlings using lists and laziness, and he's sort of exploring those ideas at the time. And he says, this paper is showing a simple method whereby programs use exception handling, backtracking, and pattern matching in a lazy functional language without any other special features. So we're thinking about using just pure functional programming language to express effective ideas, the effect of non-determinism, the effect of exception handling. So these things are typically thought of effects, but they're also pure effects in this sense. I don't think I want to talk about that. Shortly after, in '88, Mike Spivey was reading MacLean, and it dawned on him that you could program with monads. So he writes this lovely little paper, which is called The Functional Theory of Exceptions, where he notices the theory between programming and category theory. So it's not that we use category theory to model the semantics of programming languages. It's that we actually programming concept category theory as a programming concept now that we use first class. So he introduces the word maybe for exceptions. So this is the paper where that first happens. So today you saw the word options. So it maybe predated that. And he also introduced the notion of just and nothing. So this is the first time that appears, and it's sort of used all the time now. And he also uses what we call our return join, and sometimes we call this the fish operator, applies to composition, which is a slightly different formulation of bind. And he actually shows how to use that as a programming language concept from the ground up. So then we see Richard Bird, who works with these sorts of ideas in '86 and '87, working with the calculus of programming, and how we can use equations to sort of drive our development of things. And he identifies lots of useful properties, so he starts using equations as the sort of defining way in which we work with our programs. So the perspective here is that rather than just writing code and then verifying that it's true after the fact, what we should do is we should write down a specification of the program that is easy to understand, and from that specification derive some other algorithmically equivalent program that's perhaps more efficient. Or we can use these properties to prove the correctness of another program from some smaller constituent parts. So he starts looking at things like distributive laws, and these end up being things like functions over monads as well. And then Mike Spivey jumps in '89 and sees this and says there's actually a categorical approach to all of this, and sees the connection between category theory as a programming concept rather than as a semantic concept. So he says that many of the laws in Bird's theory of lists are precisely conditions for various constructions to be functors, natural transformations, and junctions, and so on. And in this paper, I explored the categorical background to the theory, and by generalizing one law and adding another, establish a completeness result for part of the theory, the idea. Right. So his work at the very end goes on to say, many questions remain open for further investigations. It would be nice to find applications in programming for some of the deeper results of category theory. It would indeed be nice. His future work indicates that monads are a promising direction. He also implements a variation of the free monad, which we'll look at later, which is basically the monad for syntax trees. So he shows that syntax trees themselves form a monad, and substitution is like an important operation that we have there. So then we get to the question of what about monads in Haskell. So Spivey was writing in Haskell, and he was demonstrating these things, but I think that paper just floated beneath the radar and wasn't really picked up. Phil Wadler saw some of these ideas and also was very familiar with Modge's work, and was able to go, oh, hang on a minute, we should really have lots of great examples of how to use monads. And so he wrote this fantastic paper, which just goes through a whole bunch of different monads and shows why they're useful. And so he shows that they're good for doing nothing, for throwing errors, throwing errors with messages, doing state, doing output, doing non-determinism. This is called the TARDIS monad, where you do set going backwards. And he says so the TARDIS monad has a strange name because it's like the Doctor Who series where you play around with time and weird things happen. And he was like, oh yeah, it seems contrived, but it arises in practice. John Hughes and I discovered it by analyzing a text processing algorithm that passes information both from left to right and right to left. And so even monads that mess around with the sequence of time turn out to be useful in weird and wonderful ways. Okay, so that's the kind of the backdrop of monads as a kind of feature. And again, I haven't really described what they are, but we'll get there later. But the idea of monads is each monad captures a particular kind of execution, a sequential semantics, so different kinds of interacting things. I think I'm okay for a half an hour, is that right? Yeah. And so one of the things that we want to do is to not just think about effects in isolation. So each monad gives rise to the analysis of a particular kind of effect, whether that be exception throwing by itself, or non-determinism by itself, or state by itself. It sort of analyzes things in independence. What we also want is a way of talking about them in combination. And so that's where the idea of monad transforms comes from. So the problem with monads is that fundamentally, they're quite difficult to compose in the theory. So you can compose their types together quite well, but then what we call the theory of the monads, the way the actual operations interact with each other, that turns out to be difficult to work with. So then came the idea of monad transformers and how that interacts. So I'd start talking about monad transformers in 1989, sorry, that's not right. They talk about, what I'm getting into is now monad transformers as type classes. So type classes are introduced, which is a kind of big idea in this paper. And then Mark Jones uses in this other paper, starts implementing constructor classes. So that's defining operations using type classes over data types, so things like functors. And he in fact defines the first functor instance in that paper. And he also introduces monads. So this is like the first time where monads are not just seen as a particular monad in a particular context, but rather as a general idea, a general programming idea with an interface that we can program to. And so we can see things like the state monad and the ST, the state transformer monad appearing in this work. So what a state transformer does, or a monad transformer does, is it starts with a monad and it bolts onto it the ability of the next monad that you might have. So you might start with a monad that knows how to do just exceptions, and then you bolt onto it perhaps the ability to do state. And so this is the kind of way that we do compositional reasoning about monads. So monad transformers are kind of the only way to make them compositional. And they involve this operation called lift, which allows you to lift the operations from an underlying monad up into the higher one. So if your underlying base monad knows how to do exceptions, and your monad on top of that knows how to do state, you'd like to lift the exceptions into the stateful world, so you have state with exceptions in the upper world. And that lifting is what that achieves. Okay, and this paper is the idea behind what we call the MTL library that is in use today. Right, that is a good place to talk about MTL briefly. Again, I'm just giving you high-level ideas. Hopefully we'll see some of these come up later on, but I'm just trying to give you a flavor of the story at the moment. So what is the basis of this problem? So I've talked about lifting operations from one monad up into another monad. So there's this weird thing that happens when you lift an underlying operation into another monad, is that there might be more than one way of doing that depending on which monad is on the inside and which one is on the outside. So if you have non-determinism, that's to say the choice between doing one thing or another, so think prologue, think giving different answers back. So think about if you want to know what the square root of a number is, so what's the square root of 4? The answer isn't 2, the answer is 2 or minus 2. There are two answers, so we have a non-deterministic solution to that. How do you interact with state? Well, you might be able to put and get variables. How does state and non-determinism interact with each other? So you can think of there being like a tree of computations, and your state might be shared amongst all the siblings in that tree. So if somewhere in this part of the computational tree you put something in the state, then this value will also receive that state. That's called global state. But you can also imagine a different world where, as you do all these forking computations, they copy the state so that any change that you make to this part of the tree doesn't affect anything over here, it just affects the subchildren. So you have like a copy of the state that you modify. We call that local state. So you've got global state versus local state. Which one do you mean when you have non-determinism and state interacting? Well, that depends on which is the base monad and which one is the one that you're lifting on top of that. So what you immediately have is this problem of like an n by n difficult problem where if you have n different kinds of monads and n different things that you want to extend by, what are all the combinations of how these things work? How do you fill in that square? And the answer is, according to MTL, you basically look at every pair inside this grid and you say how the semantics should be. So when you look at state and non-determinism, depending on which way around you go first, you get one or the other semantics. And that's really troublesome, because it means that whenever you extend your language of monads with one more monad, you need to go through every single other monad to say how it interacts with that. And that's a no-go insofar as compositionality is concerned. And that's where the idea of effect handlers comes in. So the idea of effect handlers is to try to do something about this problem of compositionality of effects. So it's important to all of us, if we're interested in semantics of the effects that we're doing, and to try and understand how we can layer our languages as being built out of different interacting effects. If we think of our programming language as a monolithic language, where everything is static, like the language doesn't change from the beginning, we don't need to think about effects at all. Like you've dealt with the problem. Your language can't change and can't extend. But if we've learned anything from the next 700 programming languages, Landon told us that what we should do is think of a programming language that can extend itself with new operations and with new equations between those operations. If we have programming language like those, we do get into the problem of what happens to the effects, how do they interact? And that's where effect handlers try to solve a problem. So, I need a bit of a drink. I've been rambling for a long time. You've been very quiet, which scares me. I'm sure there would, I should have said this about an hour ago. Please interrupt. I'll carry on nothing more. But are there any questions while I have a drink? Like I said, this is in two parts. First part is lots of history, and the second part is actually, we'll do some coding. But yeah.
Just to be sure, we haven't yet had a definition of what a monad is.
We still haven't seen what a monad is.
Okay.
They are these strange and scary nebulous things that nobody still knows how to define. So my hope is that in the next session we'll actually look at them and then we'll know what these scary things are. Yeah.
So, this monad, like, you know, you would important to one. Happens in the category of sets, it's like coming from set to set.
It's more general than that.
Oh, is it more general than that? We don't. I mean,
Oh,
the
how
category
Julian
is
asking.
like, yeah, I'm talking about Haskell.
Oh, yeah,
like,
yeah,
so,
okay, yeah.
so my question is like, it happens in the category of set from set to set.
Yes.
It's just something limited to set. That particular thing.
Yeah.
And like not in the categorical sense, like and because in that sense, is there any reason to like use the word monad itself, so like something happening in the just the category sense?
Oh yeah, that's
For example, like someone, when I was having a discussion with someone, like instead of calling functor, we could call something like mappable. That's more intuitive.
I see. Yeah. Yeah. Okay. So your comment is that Haskellers tend to bandy around general categorical constructions like filters, like monads, when in fact they're only applying them to a particular category set, and so maybe we should generalize those. I actually think I agree with that to a certain extent. So it would be nice if Haskell had a way of actually having real filters and real monads, which it doesn't right now, and that's partly to do with library design.
So, I mean, like for example, instead of calling it functor, if something called mappable, that's more intuitive, like the idea of mapping things.
Yeah.
So like someone would first seeing the thing functor, oh man, what it is. So then mappable would be like list, you could think, trees, you could map things, like
Yeah, I agree. Yeah, I think that's a good comment. Yeah, thank you. Yeah. Anybody else? You've been in input mode for so long that you've either gone to sleep or you're waiting to finish. Let me carry on for just a minute. All right. So, what's the big idea behind algebraic effect handlers? So the idea behind these things is actually quite simple. And it goes back to the story that we've been trying to tell since the beginning, which is this division between syntax and semantics. So we saw that idea in denotational semantics, where Scott and Strachey were saying the semantics of a syntactic term is given in terms of its meaning and its constituent parts in the semantic domain. So we think about syntax being something which we call the free monad for a functor, which provides the signature. Basically, it means a syntax tree. And the semantics is often given as a fold over the free monad. In other words, you inductively collapse the tree into a final value. And that's it. So because we're talking about syntax trees, I can draw these things as such. Here's a syntax tree. And I'm just going to flash up reasons why people like effect handlers. Again, I'm not expected to really understand what's going on at this stage. But the point is that they're syntax trees so we can inspect them. So we can actually look at the nodes of the tree and say, what is this? They're denotative, which means that the semantics of these trees can be given by an induction over the structure of those things. In other words, it's harder to write bugs in your code when you're handling these things because you're talking about how the nodes interact with the semantics directly. Another reason that we like them is that they're algebraic, so the operations always respect substitution and sequencing. And this is a big deal. If your programming language is weird with respect to substitution, it makes it very difficult to know what on earth is happening, and here we have a guarantee that that works out. They're also extensible, which means that the syntax trees themselves can be extended with new syntactic nodes. This is also an interesting point. So in a programming language today, you might write a language, and then in some sense, the syntax of your language is fixed. You can't add new syntax nodes to your language. But with algebraic effects, the idea is that you should be able to add new nodes, new kinds of things into your language itself, and interpret them. So we're back to Landon's 700 programming languages idea. They're modular, which means that the semantics of your term aren't just given monolithically. So what you do is you give a semantics to a particular class of the effects, and then to another class of effects, and you change things together. In other words, you can write your compilers or your interpreters compositionally in parts rather than as one big part. They're flexible, which means that although normally when you write a compiler you have a particular semantics in mind, with effect handlers you can change the semantics as you go. So you can switch in and switch out different kinds of semantics. Now, you might be wondering, why on earth is that useful? Actually, as pragmatic programmers, we use it all of the time. When you compile your code, you probably compile it with no compilation optimizations turned on because it compiles faster. When you ship to development, you do like an O2, all optimizations enabled. What you've just done is you've reinterpreted your syntax in a completely different way. You've said, I want to reinterpret this syntax in an efficient way. Or you might put it into debugging mode, where you start being able to inspect the code and freeze it and do stuff with it, which is a much slower runtime, but allows you to debug it. That's a different semantics to your code, right? Because the code that runs fast doesn't allow you to just suddenly stop, whereas this one does, and you paid for it because now it's slower, but it is a different semantics. So there are all kinds of, or maybe your code might do some profiling, so you want to see how long it takes for a particular function to run. Again, that's a different semantics. If your print statement just prints and another one prints but marks the time, that's a different semantics to the print statement. So it turns out that when we're writing compilers for things, we very often write different semantics for our programming language. How do we write that code that does the different semantics? Well, we probably have an unholy bunch of hash, if def, C statements that do pragma injections, depending on what flags that you want enabled, right? That's not the way we should be coding at all. It should be much cleaner than that, and that's what the idea is behind this. Okay. They're equational, which means the relationship between operations can be expressed by laws, so we can understand what operations are in this sense. Back to Landon. And they're pervasive, in other words, they cover a huge class of effects. So printing, getting, putting, throwing, fork, read, write, etc., etc. And then the final thing is that they're actually quite efficient because even though the theory says that you should be defining things sort of step by step, there's a way to fuse those computations into one to make things a lot faster. So that's why we like algebraic effects, and I think I'm slightly wrapping up. Yeah. I wanted to just touch on what the history is behind these things, and then hopefully we'll slide into the next session where we actually do stuff. Levert studied universal algebra and equation set. We've already seen universal algebra pop up. And John Power looks at how this is useful in the context of computer scientists. And Plotkin and Power talk about the semantics of algebraic operations in a paper in the 2000s. And they arrived at the view that computational effects determine monads but are not identified with monads. So it's an interesting pivot, right? So they're saying computational effects aren't exactly what monads are. They give rise to monads, but there's something more fundamental. What is that more fundamental thing? It's these algebraic effects, computational effects. Then they talk about how to combine things in the sense of monad transformers. And then in 2009, you get this idea of operations and handlers, where operations construct effects and handlers deconstruct effects by Plotkin and Brenner. And that's the work that we would cite today as being the sort of foundation of algebraic effects that we can use today. Where might you encounter algebraic effects? Well, in all sorts of places. So the effects bibliography has been put together by people with all sorts of citations since 2009, covering lots and lots of work. The point is they're starting to be all over the place in programming language semantics. I think there's work on putting them into WASM, so they're like first class in first WebAssembly, and they're kind of creeping into all sorts of new programming languages because they're an easy way to extend your language. So I think that's the end of part 1 of the talk. Thank you very much for your attention. Are there any questions before we kind of break? Thank you so much for your patience. I think you have a well-deserved break. And you can resume next time. See you in a bit. Okay, so this is where we could sort of choose your own a bit. What I have here is a slide deck that goes into a slightly more practical angle on what algebraic effects are. So it just sort of demonstrates how they might be used to mess about with some programs. And I suggest that we just sort of look at that just so you get a sense of what the game is that we're playing. And then I think this will probably take about maybe 40 minutes to go through, maybe half an hour or so. And then after that, we could probably do like a classic just monads tutorial, because there seems to be some desire for that. So that would be a good time to step out the room if you're bored stiff and don't want to learn any more about this stuff, which I would never feel offended about. So does that sound like a reasonable plan? I just realised that it's impossible to ask a question like that and for someone to go, no, it's not, do something different. So let's just carry on. Okay, so, right, interpreting operations. So, where are we in the story? We've arrived at the point where we want to talk about effect handlers and sort of know what they are. And so, here is a program. It's in Haskell, sorry, surprise, surprise. Jeremy pointed out earlier on that we were in Glasgow, I should have said. So GHC is often these days referred to as the glorious Haskell compiler, which you would use, but it is not the glorious Haskell compiler at all. It is the Glasgow Haskell compiler, and so I'm well in my rights to go on about this the entire time. So here is thank you, Gary. So here's a program which just does something a bit banal. It's counting lines. Is what we're going to go for. So it's an echo program. You get some string from the terminal. You have a look at that string. If the string is empty, then you finish your program. Otherwise, you put that string out to the terminal and you echo, which means you carry on. So this is just going to go round and round, echoing what's already there. Okay, so why is this program interesting? Actually, it's already got a few features which are typical of algebraic effect systems. So the first thing to notice is the type of this program, echo. It promises to return unit, which means when it returns, that's the return statement there, it returns the unit statement. But notice that here there's also an effect annotation. So many of us will have been trained already at this point to do type annotation style programs. We know the difference between doubles and ints and bools and characters and whatnot. And we typically think of that as being a good idea. Not every computer scientist thinks that types are a good idea, but many do. And amongst those of us who do, I think the reason that we like types is because we do a kind of unit analysis, right? You can't add liters to centimeters. It doesn't really work very well. And so we want to do a kind of unit analysis with our programs to catch easy to discover bugs. When we write something like this, we might annotate the program with the kinds of operations that are in scope, the kind of operations that are in play as well. And this is also like typing, but it's not typing the result of the computation, it's typing what this program might interact with. I've got the example, but I'm not going to bother putting it up, it's a bit of a waste of time, of a Python program, not pointing my finger at Python particularly, because it's lack of types or anyway. But I've got a Python program and a program called bad, right, which adds things badly, right? So the way this program works is if you do bad 3 and 4, it will give you 7. If you do bad of 10 and 5, it will give you 15. Bad of 1 and 7, it will give you 8. It seems all okay, right? It seems to add. If you check all the bads from 1 to 100 added with all to 100, it gives you all the right answers. So all the unit tests pass the first time. If you do it again, it will fail every single test that you've tried to add something twice. Why? Because I've got a bit of state in there that remembers the things that you've passed in, and it just checks to see, it puts them into a set, and if it sees the same addition, it will do something bad and just return 0, whatever it likes, right? So there's nothing wrong with that program from the outside. Imagine if we had a well-typed Python program, and that thing told you it takes 2 integers and returns an integer. It doesn't tell you anything about what it does to the state. In fact, you could well imagine this being a Java program or a C program. And what's bad about this program is that it's not doing what you'd expect it to do, because I think of addition as being a pure computation that doesn't say what's been added, so that it can mess about with what you've added later on. Right? That's a stupid thing for it to do. If the effect signature told you, by the way, here's addition, it takes 2 integers and it returns an integer, and it modifies with a big stateful map that contains all these integers, you'd probably raise an eyebrow and go, why is it doing that, right? And so this is the kind of philosophy that we have here, is if you knew what your programs were interacting with, maybe you'd be a bit more suspicious about the kinds of things that they're doing. Maybe you'd catch a class of bugs that was sort of latent. So here's a program, it's echoing, and it promises to work with getLine and putString and nothing else. So it promises that it's not going to interact with your files, it's not going to interact with, I don't know, your network, and it's just going to do these 2 things as well as pure computation. So that's kind of an idea that I don't think we see in very many programming languages today, but I think is going to be an important feature of programs that we trust. So can we do effect annotations on our programs coming to Cinnamon? Right. How can we track the number of times putString is executed? So I shouldn't have made that rhetorical. I should have made that a thing to rouse you from your sleep. Yeah.
Hello. I know WebAssembly and things like that have kind of capabilities, so you can say dynamically you're only allowed to do these.
Yes.
Is that sort of the kind of dynamic equivalent to the static thing we could do here?
Yeah, that's right, exactly. Yes, we're seeing it creep in. We're seeing it creep in what's that other thing that LLVM has its compilers down to? I forget. So we are starting to see that in certain languages, where there are sub-languages being pulled in, and you can see that. Yeah. Yes.
Just relating to what you were saying about our Python program,
yes.
We could type it. Does this not raise a question of, we might want to have something that is pure, but we want to memorization?
Yeah.
Do we not need to be careful to allow us to still do that without leaking?
Well, so I think that it's a great question. The question was, what about if we want to memorize our pure functions? And I would argue that memorization has the side effect of growing the state, right? And so maybe you're state sensitive and you want to know how big your state is. So maybe it is a good idea to say, I will memorize no more than 40 gigabytes of memory, or whatever it is. And so yeah, but that's right. I think that at least having the vocabulary to talk about that is important. So whether or not we use this to its full extent and everywhere is a different point. Are we measuring the amount of energy that's being used in this function or not? We could, but I'm not making any promises about that in this one. So I think there's lots of scope for at least having the ability to talk about these sorts of things. Yeah, thanks. Anyone else? Yeah. Yeah.
Well, for types and exact specifications,
yes.
But there is a kind of a reason there's this dichotomy and allergy to types, so
yes.
People advocate that, but this is even more types.
I know.
So
they better give us something. Yeah, exactly. So we are widening the schism. And Conor McBride gave a really great talk ages ago, and he said something like, what are types for and what are types against, was this kind of pitch. So we often think about types as being against all sorts of stuff, like don't make these mistakes, don't do this, don't do that. But what are they for? They're actually for program optimizations and that sort of thing as well, right? So they're for program generation. And I think we can play this, we should ask the same question here. So what I'm just focused on here is, what are effect annotations against? They're against us doing stuff that we weren't expecting. What are they for? And actually what we get out of this is basically a well-behaved macro rewrite system. So because we know that we're interacting with getLine and putString, we're able to intercept those operations and do different things to those, which comes back to the thing I was saying earlier about having your compiler run in different modes, so in optimization mode or debug mode, etc. You could imagine now introspecting getLine and putString and doing different things to those. So you're absolutely right that there is going to be a widening schism between people who do effect annotations and people who don't. My hope is that, again, it's not just about telling people they're naughty, it's also about telling them what they can do with these things. And maybe that will be alluring enough to even those who don't like to be told they're naughty. Yeah. Okay. Yeah, so back to the question. So imagine if you were asking this to a first-year undergraduate doing computer science, right? And you look at this echo program, and I want to count the number of times put string is evaluated. What might they say? They might say, modify the program, right? And we all know that's a bad answer, but let's run with it for a while. Why is it a bad answer? Because we know that as software engineers, if you've got code given to you by a client, and the answer when you want different behavior is modify the code, that's not very backwards compatible. You want to be able to somehow change the semantics or something without modifying it. So the problem is your code wasn't parametric enough or something to start with, right? But let's go with modify the program. Okay, so we'll modify the program. So what we're going to do is we're going to add a new operation, this one called tick, and what it does, it allows you to say tick after you've written your get line, and this is a single operation that emits nothing, and never mind what it does too much, it's just a piece of syntax at this stage. But the point is that we're annotating it with this ability to tick. Okay. And so now here is a picture of a sort of mental image of what it means to use effect handlers. I like to think of these things as, have we got it? Christmas tree consumers. So you've got a syntax tree on the left-hand side, it's your Christmas tree. And you've probably seen these machines when you bought some Christmas trees, they look like this in the real world. You put your trees through them and they come out all wrapped up. So effect handlers are essentially like that. Your syntax tree is the program that you've written here on the left-hand side. We're going to shove it through this machine, and what's going to come out on the other side? A tree, right? Is it the same tree as before? Well, no. It's now got stuff attached to it. And it might even have lost a few branches along the way, right? So that's very much what's going on here. We have a syntax tree. We're going to we're going to annotate the handler, which is this big thing in the middle, with several different things. So this is a handler. It recognizes and removes any puts and gets that it finds in the tree. So any put and get in this tree will be annihilated when it comes through this. And it adds to the tree, in this case, nothing. But it could, in principle, add stuff to the tree as it goes through. And then these two parameters are there to scale. So the third parameter tells you that it interacts, or the domain of effects is augmented with state T things. In other words, we're going to add some kind of states to this program. And then the final argument here tells you how the pure result is modified. In this case, it says that the pure result will return you that state. So these things are often very related and tightly coupled, but they can be a bit more loose than one-to-one correspondence. So just to reiterate, this parameter here tells you that we're going to transform the state we're going to transform the ambient effect world by adding state. In other words, we're going to add some state S that holds what we're getting put up and storing. And this thing says, at the end of your computation, we will tell you what that state is. So you can imagine a version of this where we do modify the state internally, but we don't tell you that we modified the state at the end. We don't tell you what that new state is. For example, my bad example earlier on, where the adder was modifying the state, but it didn't tell you what the final state was. That would be an example where these two things differ. Okay, so the tree goes in, and what happens is that the program started looking like this. It's got the gets and puts in it, and in the end of it, it's got nothing in the output. But the pure result, which used to be an A, is now attached with an S cross blank. That blank becomes the A. So now you've got the state and the pure result coming out. Okay, so that's just me labeling some stuff and saying, okay, so we're going to do something to the tree, we're going to do something to the pure value that they will kind of pass through. That's the kind of mental model you should have. Okay, so let's look back at our program. So the perspective of these programs is that they are just bits of syntax. Now, I think that when most people look at programs, they immediately start executing some kind of semantics in their head about what's going on in that program. And that's something you need to sort of slightly untrain yourself from doing when you're working with the backhanders. You should look at the program syntactically and think, I wonder what it could do. It could do this, it could do that, it could do the other. And then it's up to you to decide what it does by offering a handler that will deal with that. So here is a very simple program. Never mind too much about this line. It's basically how tick is implemented. But there are two different handlers, at least two, that you could apply to this tick to deal with it. So I lost a screen. this handler recognizes the tick operations in the tree and removes them, puts nothing on a tree, doesn't interact with any kind of, doesn't change the ambient monadic state, and doesn't do anything to the pure output. In other words, it really just removes all the ticks and doesn't do anything else, right? And you can kind of see that from the signature of the handler. This one, the ticker, is the one that's actually going to count how many ticks it sees. So what does it do? It removes all your ticks from the tree. It doesn't add anything else. It promises to actually interact with state somehow, and it even tells you that it's going to output back a state, or a number, which is presumably the number of ticks that it's seen. So these things are annotating with a bit more detail what's going on inside the system. So the way that these things are implemented, and I think that the implementation details aren't really that interesting here. There is some code you have to write which says something like, if you see a tick, then please just do nothing. That's the unticker. There's some machinery that allows you to define that, and I don't think it's too relevant to do it today. Then there's this funny thing called handle IO, which basically says, I'm going to try and apply your handler, which takes in, that recognizes and removes the effects, produces some output effects, and a program that has those effects embedded in it, unioned with some IO effects, and I'm going to execute. So why all of this extra mess? So let's try and understand what's going on. The handler will recognize all the Fs inside the program, but there might be also some additional effects in the program that the handler doesn't know what to do with, some additional IO stuff. And the IO handle IO says, so long as those IO effects so long as the output effects are a subset of those IO effects, I'm perfectly fine with the handle outputting even more stuff into this IOS, and I'm going to just shove it all out to IO. So what this means is that we're deliberately saying there's a class of effects which we're not going to touch. You can do as much of that as you like. So a little bit like the question that we had over there about, what if you wanted to do memorization but you didn't want to keep track of memory or something like that? That's where you can bundle those kinds of things. You can pass things through and say, well, these ones, I know they're happening, but I don't really want to know about it anymore, so just pass it through. Okay, so that's what the handle IO does. And it allows you to actually interact with the real world in this system. So if we were to do handle IO, which is this thing, applied to the unticker handler, applied to the echo program that we saw earlier on, we type hello, it echoes hello. We type world, it echoes world. We type a new line, it outputs empty unit. We're done with the computation. And that's the unticker program. It hasn't interacted with the tick at all. Like, it's nowhere to be seen. So we're now going to just have another little example of a different kind of effect before we go back to ticker. So this is the effect of getting and putting. So here we have the get operation, which says, I'm a family of programs that know how to get some state, and I will result in that state out to the user. So this tells you, the effect annotation. Everyone can say get, well, this is get. And what's the output of this? It's an S. Whereas here you've got, I will take in a state as a parameter, like put 5, and then what I produce is a program that knows that says I will put stuff, and it outputs unit. There's a pure, it returns nothing to the user, but we know that it's interacting with put somehow. Does it actually interact with a state? Well, that's not the operation's job to tell you. The operation just tells you, I'm this operation and here I am. It doesn't tell you, and here's what you'll do with me. Remember, the ticker, the tick in the ticker example may or may not interact with state, depending on whether you record it. This here is the state handler, which says, I recognize put and get operations. I don't add anything to the tree, but I will interact with the ambient context of effects by adding states to it, and I will also give you the final state out. So you can kind of guess what state does. It thinks of put as putting to that state and get as retrieving from that state. There's no guarantee of that, but that's what we do. To be kind of more honest with you, in the algebraic effects world, we would normally have a bunch of laws associated to get and put that tell you things like, if you put to the state and put again, the second put prevails. If you put to the state and get, you get what you put back. If you get and get again, you get the same thing. These kinds of laws you would normally state. I'm not bothering with any of that, but that's something that real vector handler systems do. Okay, so if we handle, so this time it's not handle IO, oh, no question, yeah.
Probably in the so if I see Pascal as like an extension of system and
Yeah.
formally, and basically my question is how do I formally see the handlers like in such a setting, and you get my point, like how do we integrate into the theory of the system, like for example extend the thing so that I can talk about the thing.
Okay, we have a whole paper about that, so maybe we'll talk about that another time. Yeah. Yeah, thanks. So the question was, how do we formally account for this? But yeah, indeed we can. But I won't go into it. Yeah.
This may be a stupid question, but is the brackets on the right side and the pair, the output pair, is that the state that it ends up with?
This one here?
No. Within the handling in the actual interpreter, down at the bottom.
Down at the bottom. So up or down?
In the GHCI.
Oh,
console.
down here?
Yeah. The output is 42,
Yes. Okay. So that is the first component of that is the state. The second component is the pure result. And so what you'll notice is that the pure result of the program. So the program that we're dealing with is this get put program. Put promises to return just unit type, and the handler here says "S," which means pair up the unit type with an S, and that's why you get back down here a number 42 with the unit type.
Thank you.
You're welcome. Okay, so here the handler is a pure handler. It doesn't interact with I/O. It just interacts with the state context, and it says something like, if you execute the state with 41 to start with, then you get, and then you put plus blah, 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 and you get 42 back. So it sort of does what you know. All right. So how are these things defined? Well, this is all boilerplate code that now users don't have to type anymore because it's all automatically inferred from a signature. And again, the point I want to make here is that there might be different versions of the state. It's not too interesting what the code is down here. What's interesting is this particular one wraps up the final state as the value, and this one, it's empty. So in other words, you don't actually see the state when this one executes. You just sort of, the state just interacts with your code in some way. And this is how you would actually evaluate these things. That's more for people who are interested in the details. It's not too interesting otherwise. But the point is that it does some pattern matching on the putting and the getting, and it rigs in some values and counts on. Okay, so now we can start writing a different handler by doing something like this. We can say, I'm going to make a handler. It recognizes tick operations on your tree, and it outputs putint and getint operations. So in comes your tree with the ticks, out comes your tree. It's got no more ticks in it, but it does have put and get. So we've modified the tree by adding things and removing things from it. And so how does it happen? Well, if you see a tick, then get the state X, then put one more, and then return. So you can see the tick's now gone because we've pattern matched on it, and we've added to the trees two other operations. And what's kind of happening behind the scenes that sort of makes sure that you're not doing something totally crazy is this, this parameter k is the continuation that tick promises. So tick is saying, once you tick, the program will continue with k, whatever k is. It's the rest of the program. And the type system, the way that this library's been designed is that it's not going to let you get away with not evaluating that k. You're going to have to use it somewhere, somehow, and that's it here being returned at the end. So that promises that you're not going to suddenly forget to do the rest of your code. So there are constraints on what you can do to the trees. And these constraints exist in the way it's been implemented to stop you from doing silly things like running through your tree and just reorganizing things in bad ways. You can sort of know replacement and replacement, so removal and insertion, but you're limited to a sort of sensible space.
Sorry, what exactly? Right,
Sorry.
So it's all cool that so we were forced to run a handler with actually using the configuration map that is fast with the network. What exactly in the description code is so where is that constraint?
Yeah, good question. So if I answer your question, it's what is it in here that forces us to make sure we use the k? There's nothing that I've shown you that would make you believe that, apart from.
So why?
So the way the library is designed is that that should hold true, and the way it's actually working under the hood is because that type parameter x is an existentially bound variable.
Okay.
Does that make sense?
No,
Oh,
but,
okay.
but I say it's outside of the whole effect thing. So.
Yeah. So basically, what's going on is that the alg here is saying, I'm going to consume programs whose result is some type x, but nobody knows what that x is, and I'm going to ensure that I make programs with that
Alright,
x.
so I can't just synthesize some random thing of like x because I don't know what it is. It's not possible. Okay.
You got it, exactly. So because you don't know what's coming in, therefore, in order to make sure that you guarantee it comes out, it must be that you're reusing the garbage that came in. So garbage in, garbage out, and k is the garbage here. Yeah. So yeah, good question. Thank you. So the machinery is designed so you can't mess about with things too much by using this kind of trick. And something about this library, I mean, this is very much an experimental library at this stage. The type errors that come up with this are absolutely horrific. So if Azalea is worried about people not adopting this because they don't like types, like this will immediately make them completely allergic, right? So anyway, it's experimental. So far we've looked at handlers in isolation. What we might also do is start mixing handlers together. So you can imagine a handler that deals with certain parts of the syntax and produces some syntax, another handler that maybe consumes some of that and produces some more. And there's a whole pipeline of these things going on together. So we have a bunch of pipeline combinators that puts them together. Yeah. Okay, just hanging out. So this here is what we call the pipe operation. What it does is it takes two handlers and it just sort of shoves them together. So the output of one goes into the input of the other, and you can put them in connection. So the ticker handler here that I should point to this thing here. So the tick handler that recognizes ticks and does nothing with them. Removes ticks, adds nothing to the tree, but interacts with state and tells you how many ticks are back, is the tick state handler that we saw earlier that takes ticks and creates put and get operations, followed by the state handler that takes those gets and puts and interacts with the state with those things. So now we've got the compositionality of effects coming into play. We've got a kind of new semantics coming out of two semantics composed. So now we can say handle ticker echo, hello, hello, world, world, and then 3 comes out because we entered 1, 2, 3 lines, including the empty one. And so the program worked. Wonderful. But let's go back to the original question that we asked our undergraduate friend. How can we track the number of times put string was executed? And they said, modify the program. And we said, modify the program? Are you mad? Don't modify the program. We should never do that. What we should do is we should reinterpret getLine, right? So what we can do with handlers is we can say, don't bother with the tick. Why don't we make getLine automatically always do a tick increment by itself? So you can imagine that what we do is if we see getLine, please re-emit that getLine, but also increment the state and then carry on. So now we've given a different semantics to getLine, and the original program didn't need to be changed at all in order to have this behavior. Yeah?
Isn't that still in some sense changing the program, though? Or are we just, I don't know.
Yeah, we absolutely are changing the semantics of the program, but we're not changing the syntax of the program.
Okay.
So I think the point is that from a sort of, dare I invoke Java perspective, you've got this close to modification open to capital. I'm sure there's a time for that somewhere, but the point is that the syntax is the same syntax. That could have been delivered to us from outside, and we get to introspect that and change it.
But getLine could have also been delivered to Java. But that we changed getLine.
Okay, but because the program told you it was using getLine, it's giving you permission to do what you want with it. So it's the what they're for part of the argument. Yes.
Hello. If you did this 20 years ago, I would have said you did expect your rigid program.
Yeah.
This is joint points. Do you recognize that?
Yes. Yeah, that's right. Yeah, and so I think we're coming back to this sort of thing again. And like I said, this is a sort of well-behaved macro expansion system as well. So it's yeah.
I'm a little bit confused what state T is there.
Yes.
It is like a factor you're using within the scope, or I don't know what.
Yeah, great question. Yeah, so the question was, what on earth is state T doing? So the way to think about it is your program comes in and it interacts with a whole bunch of effects. It could be interacting with the network, it could be interacting with non-determinism and all sorts of stuff. I don't know what it is, but there's stuff there. And what state T is doing is saying, whatever that stuff is, I'm going to add to it an integer, and a state integer. So the state T is promising that the ambient effects has been extended by something. And it's kind of nebulous because I haven't told you what state T is, but the definition is that. But the point is that there are different kinds of transformers that you could apply to that ambient effect. So you could say, I'm going to add to you non-determinism, I'm going to add to you the ability to look at files, or I'm going to add to you the ability to throw exceptions, or etc., etc. So these are all different kinds of T's that you could apply to the inner part.
The way you're saying it, it kind of makes me think it's like some co-effect situation. We have input effect, output effect, and then a co-effect, which is something that really uses the world.
Yeah, that's absolutely related. So by doing this, we're sort of promising that the world is offering you a bit more ability than you had before. Yeah, there are definitely co-effects going in. Yeah, good observation. Yeah. Okay, so in this piece of code, where are we? We're promised that we're going to do getLine incra, which says that every time we see a getLine, we get input, and then the state is going to consume that get input, which means that we actually don't have it on the output side anymore. We still have the get lines, so they still need to be invoked by somebody. So somebody needs to tell you how to do get line. But because we execute this in handle IO, any residual IO-ish stuff gets sucked up by the handler and will be executed. So it goes, oh, get line, well, that's an IO thing. I can just let that through. And so you get this behavior that we'd expect out without modifying the program. So pure programs. One thing that you might want to do as a developer is test your code. Maybe you don't like it that you've written a piece of code and in order to test it, you actually need to interact with the IO prompts to enter the information and get information back out again. And this program says, well, what we'll be getting from the line inputting strings, and so you think, well, I'm kind of stuck. But actually, because we're in charge of getLine and putString, we don't have to interact with IO in order to do these operations. We could just inject our own input and pull out our own output in whatever way we like. So if we want to test this program, we might give it a handler like this one that says, I'm going to suck up any getLine and putString in the tree. I'm going to I'm not going to add anything to it. And what I'm going to do is I'm going to allow there to be some interaction with state. And I'm also going to provide you a way of writing some list of strings. And again, there's no kind of formal specification here about what those two parameters are, but in the back of your mind, you should be thinking, this state T is the stuff that you're getting from the line. So this list of strings is the strings from the user that they're passing in, and you're allowed to remove things from that string as you go through, so it needs modification. So if you inspect that string, read some stuff, the string, the input string has changed, it's now smaller. And this writer part here is the stuff that you've logged. So the put string stuff has been putting stuff out, it's been writing to some log of strings, and that's what this writer T environment tells you. Because those things, these two things, the input string, sorry, the state T string and the writer T string, they represent different parts of the state. This state T string represents the input string that's being consumed and modified as you go. This write string is an output string that somebody is logging and writing that you're able to write to. And then at the end, you get back the result of the state in this particular version, so you can see what the unconsumed input is. Okay, I think we've talked about all of that, and the idea is that if we do handle teletype hello world echo, you get back hello world as the, oh sorry, I think it says something wrong. Hello world is the output thing that you've been logging, so we logged that hello world came out. So this teletype takes in the input string, and here you see that it's been faithfully reproduced. Fine. I think I'm going to skip through this. It's not terribly interesting. We're just saying that state is another, state underscore is the handler that modifies state and then secretly doesn't modify the pure result. So that means that it is keeping track of the state, but nobody sees the state. No, you can't inspect the state at the end, but you will obviously see the result of the state, how you modify things. Pure output, this is me just saying what writer stuff is going on. I don't need to know that. And then this is how you put teletype together as the composition of different effects handlers. So the point is that we can composition in the way we build these semantics. So bigger semantic blocks out of smaller ones. All right. Did I hear something? No. Okay. So we're going to change gears now a little bit and step away from algebraic effects and step into what are known as higher order effects. So somebody at break time said, hang on a minute, Nick, that list of operations that you put down earlier on, were they deliberately missing things like local state? And the answer was yes, there was a whole class of operations that we just can't deal with in an algebraic manner. I haven't defined what algebraic manner means, it just means it works well with regard to substitution. So there are operations that behave a bit weirdly with respect to substitution, like catching errors. So if you have a program and you catch some errors, catching itself does some strange things to the program flow. Other examples would be if you have a non-deterministic a tree of competition or computational results, and you want to do something to that tree. So if you output the whole tree, it's fine. But if you then have like a way of pruning that tree, so maybe you're just going to get the leftmost node out of that tree, perhaps you're going to get things of depth 5, perhaps you're going to get the first 20 results. When you start messing about with the continuation structure, that's no longer algebraic. But that's a perfectly fine piece of syntax. You can imagine your Prolog programmer wanting to take the first 5 results of something. Why shouldn't that be up for grabs with this system as well? So these are all examples of what we call higher order effects. Programs that take programs as parameters, and you expect them to interact with those programs in their parameters, but you also want to be able to adjust the way that interaction works. So let me give you an example of this. So here is a function that will retell. So what retell does is if you say tell w, in other words, you output w to the logger. What retell does is it takes a function f and it will just modify that output. So perhaps you want everything to be in all caps rather than as it was. Perhaps you want to remove all occurrences with the letter y, whatever, and you can do that. So for example here, if you do retell map to upper on the writer handler, then get bigger will just modify its output. So the thinking here is if you might want to add a cipher to something or all sorts of things. So I've got 4 kids, they love stories, and one of their favorite stories is SEO Trot. SEO Trot is a strange story, as most Roald Dahl stories are, about a lovely gentleman called Mr. Hoppy, who has a problem. He's madly in love with his neighbour, who's downstairs, and she's madly in love with her tortoise called Alfie. And she desperately wants it to get bigger, and so he devises this very devious plan to keep replacing that tortoise with bigger tortoises without her noticing, so that in the end she'll marry him. Oh dear. Anyway, but the cool thing about the story is that he comes up with a way to make it seem as if it's plausible, which is to say, he speaks tortoise language. And when he speaks to this tortoise, he says, SEO trot, teg regid, igok no, SEO trot, wog poo, fuck poo, tush poo, and so on. What on earth does this mean? Well, he knows the secret to talking to tortoises, which is that you have to A, shout to them, and B, talk to them backwards. So if you reverse all that, it says, tortoise, tortoise, get bigger, come on, tortoise, puff up, shoot up, something like that, right? So, okay. Now, Mr. Hoppy is really trying to make him grow very bigger, and so what does he want to do? He needs to speak in all caps and backwards. How will he achieve this? Well, he's going to use modular higher order effects, of course, right? So what does he do? He's going to write a program. He wants to say something like, hello Alfie, tortoise get bigger and goodbye. right? So here's the code that he writes, and then what we're going to do is we're going to construct some operations around that. That's tell, and it's the same operation everywhere. And we also want to censor what he says. So we want to censor everything inside this censor operation here gets done backwards. So tortoise will be backwards, and get bigger will also be backwards, but goodbye will not, right? And then he obviously wants to censor some of it to be in capitals. So he's going to say SEO trop in small, and then get bigger as the emphasis that we have here. Why is this an interesting example? It's because we have sort of nested operational modifications to the program going on. It's a real mess. How would you program this normally? We might have like lots of if-then-else flags flying around, etc., but we don't want that, right? We want to be able to just say censor the text that's going on here in this local part. Okay, and then so how would you write that? Well, in this system, you just basically write this, and then you write handle, censors to writer, copy, bang, out comes the output that you wanted. Wonderful. But suppose, Mr. Hoppy wants to make sure that he's actually sending the right message. Perhaps he's misspelled get bigger. Perhaps he's done something wrong. He's not really sure. How does he inspect this code? Well, he clearly wants a different way of handling this program so that he can actually see what the output was. So what he can do is, rather than running the censors handler, he can run the uncensors handler. So you can see in plain text, hello, Alfie, tortoise, get bigger, goodbye, without modifying the input code. So again, we're seeing interesting applications of effect handlers which allow you to have different semantics on your code, perhaps because you want debug, perhaps because you want things to be more efficient, blah, blah, blah. Right? Okay. Okay, so I think I'm just explaining what the first order versus higher order. So first order effects are things like tell. The key indicator that it's first order is that it's perfectly fine to have some simple operations, and the inputs to these operations will be quote unquote constant things, right? So numbers, strings, just data as you see it. Whereas, and it's fine that we also have these different parameters. Whereas higher order effects, like censor, they take parameters like strings or functions as well. That's not a problem. But what they also do is they contain programs as their payloads. So what censor does is its second parameter is it's taking a program as a parameter, and that's something that simple operations can't do. So this is the sense of higher orderness, because you can take programs as an input. And of course you can take programs that take programs that take programs and so on. And that's why we're able to nest these sensors inside the system. So first order effects obey algebraicity law. So when people talk about algebraic effects, the algebraic in that is precisely this property that says if you have an operation with n arguments or n continuations followed by continuation, so n continuation followed by some continuation, then that's what distributes through. That means that you kind of attach the rest of the program to continue through all of this. So for example, throw has no continuations, find k, nothing happens, it gets deleted. If you have or, which are non-deterministically good between options, well, you have to continue through each of those options in an algebraic or. That's just a typo. If you have put s followed by some program p, then you bind k. That's the same as doing put s of p followed by k. So parenthesization here is put s p by k is put s of p by k. And then similarly with getting, if you have a program p followed by k, then the k can go inside, and so on. So that's that's what it technically means to be algebraic. And tying back to what we said earlier on, all of the monotrans stuff, so the monotransformers, can live for free. But higher order effects don't obey this algebraicity law. So catching is an example of a program that. So basically the idea of catching is you run a program P. If it succeeds, you just carry on with K. If it fails, then you want to do Q. Right? Sorry. Yeah.
How do I understand the equality between like these things?
What you mean? What is equality?
Equality, yeah.
Let's say, I laugh because obviously we talked about equality being a big problem for computer scientists earlier on. So effect systems tend to come with equalities, as in you could just state there are certain equalities that exist.
Primitive as a primitive.
Yeah, exactly.
Okay.
Yeah. So there's just primitive equality going on here. Yeah. So yeah, yes, let's stay away from questions about recursion, etc. Yeah, but the problem, so let's go back to the question here, which is, right, so we're trying to catch. So catch takes a program P, which you try to execute. If it fails, you do the program Q, and then you carry on with K when you're finished. But that's different to this program here, because how does it go? Suppose suppose K can fail. Suppose you can start executing for a while, and then something bad happens in K. Well, this program on the left-hand side will do P, and then all of K, and then that's fine. And it doesn't execute any of Q. Whereas this program on the right-hand side runs P, everything's fine, starts doing K, fails, and then the failure gets caught, and then Q executes, which it didn't before, and then some of K happens again, right? That's clearly a different piece of code. So algebraicity does not hold for this program in the same way that it did for other programs. And that turns out to be theoretically difficult to deal with, but we did. And so that allows you to write things like the censoring and this uncensoring operation, and yada yada. That, I think, terminates where I want to end up. So I don't think it's really interesting to go through all of this code and show you how it's done. I think it's kind of just lots of plumbing that says how it all works. That's all I've got in terms of slides. I'm conscious that I've been yakking on for quite some time. It's 4:30. What shall we do? I can declare it playtime for those who want to go and have some fun and who don't want to do more theory stuff. And I can declare it, let's understand what monads are for those who are interested. But we can do other things too. We can start playing with the effect system and seeing live coding of it if you want to. I kind of think that's boring. But we can. It's really up to you. Can I have a show of hands? So does anyone have any other suggestions or questions that you want me to look at first? No? Okay. Who wants the monad tutorial? Who wants the playing with the terminal? Nobody. And who wants to go and play outside? I'll see you later. All right, so let's do a quick monad tutorial. So I've kept monads quite nebulous up until now.
Is something that we also introduce in current languages, or is it something inherently functional?
You've absolutely nailed it, Zena. So I think that you can and people have implemented algebraic effects into direct systems. So I think Dan Beacon and others have written something for C++ that incorporates effects, and that's quite imperative. So yeah, there's no reason not to do, basically. It just offers like I said, a clean system for interacting with program code in some way. Yeah.
Are they as clean and nice in C++ as they are here?
Are they nice here? Yeah, I think the answer is it's all quite experimental still. Yeah. I think it's not so bad actually. Like if you're used to reading C code. Okay. So I want to just gauge roughly where we're at in the room. I will probably be writing in Haskell because that's just easier for this kind of thing. Who knows Haskell to read at least? Okay, I'm actually really looking at those who are putting your hands up. But okay, so I will do my best to sort of explain as I go. This hour is really for you, so please just stop as much as you like. I'm going to be making this up as I go along, so like, please, if I make some mistakes or get confused or skip some part of the story, just slow me down and tell me to do it again, okay? Yeah. So the thing that a monad is for understanding sequential composition. So you would normally, is it working? Yes. So I'd like to start with something like this. Normally, we think of sequential composition of programs as being this semicolon that does something like this, which means please do all of P, followed by all of Q, followed by all of R. Well done, you've done your sequential composition, right? But what is the property that we really want from sequential composition? It's something like this. If you actually did all of P first, followed by Q, followed by R, right? That should be the same as doing all of the P followed by Q, followed by R. That's my interpretation of what it means to be sequential. And monads capture this idea in a particular way. Now, the interface that Haskell uses is via a strange operation called join that has this property built into it, but through quite a convoluted way. So in Haskell, there are different ways of writing join-like operations, one of which is the fish operation, which would look like Q, R, and then this is basically taking the place of semicolon in a particular way, right? But for various reasons, this isn't the operation that's given by default, because it's just a bit awkward to work with. So the type of this fish operation is actually something like this. It's if you give me a program that takes input A and produces MB, so M is like the monadic context, B, and then one that goes from B to MC, then I'll give you an A to MC. So the way to see it is, like, this is your, is that little red dot even red? Can you see that? Yeah. So this is your input A, and this is going to produce MB. Now, what on earth is this MB going on? So the idea is that we're going to output B in some context M, where context means these are the effects that are in play, they're denoted by M. So it's a family of effects M. And here's another program that says, give me a B, and I'm going to output something in a family of results, MC. And then what I want to generate when I put these two programs together, so this might be my program P and my program Q, is I want to do like P fish Q come out, and that should say, give me an input A that's pure, and output an MC that's pure. And this fish operation has an the associativity law is exactly this for fish. It says, P fish Q fish R equals. Okay, and that holds true as the law. So in this sense, monads always have a fish operation, and so they always have this idea of sequentiality built into them automatically. There's another thing that you would expect to happen with sequential operations, which is if you do something like return X fish Q, that should be equal to Q. In other words, what does return mean? Well, return means please generate the value X in the monadic context, but without doing any funny business, right? So just make me a pure value that has an X in it and do nothing bad. And if you follow that by Q, is that right? Sorry, that is actually wrong. Oh no, I haven't got a razor on this pen. Sorry, that was wrong. So that's correct. So if we do the program that returns followed by Q, should be Q, and then vice versa, if we do P bind return, that should be P. Okay, and I haven't really defined what return is yet, so let's talk about that. So what is return? It's something of type A to MA. So it's basically, it takes in a value and it produces that value in the monadic context in a pure way. So I've talked about this in very abstract terms. I think it's quite useful to actually look at some concrete monads now. But the thing in the back of your mind is that all he's talking about is composing things sequentially. What's the big deal, right? If that's your reaction, it's the right reaction. So it feels like I'm making a big deal about this stuff, but this is this is why you'll come up with your own tutorials later on and say, well, monads are just burritos, okay? There's nothing special to them. Okay, so let's look at some examples of monads. So there's the identity monad. So these are things that replace the M. So what is the identity monad? It looks like this. So if we have some, I'll use data. So what does this mean? Oh, I should probably not call it that. I'm going to. So this is a terrible Haskellism where so what I'm doing here is I'm declaring a new data type called identity A, and I'm producing that with a constructor called identity A. which confuses the heck out of beginners because now the data type is the same as the constructor type. When you're good at this, it's like the most obvious thing in the world to do. When you're just beginning, it's like being super mean to you. So I'm going to write make identity as the thing that constructs an identity instead. Did you have a hands up?
Yeah, I think this is it's getting the more accepted way of doing this.
It's
Especially with regards of dependent hash which is coming at some point, that will be a problem. That's coming.
Yeah.
So
just to be clear, what am I doing here? I'm creating a new thing called a constructor. It's a value of, which is called identity, that given something of type A produces identity A. So this is a slightly different notation that I could use, and I probably will use that one actually, that I think is less confusing. So I should start with. So what I'm saying is, here's a new type, it's called identity A, and here's how you make it by applying this function to an A. There's another monad that we might have a look at, which would be something like the maybe monad. I'm going to show you how they're monads in a minute. I just want to get a flavor for them. So maybe has two ways of constructing. You can say nothing. Or you can say just, and then you give it an A, and it produces maybe an A. Then let's have a look at another example. So the idea with the identity monad, what that will end up being is literally like function application. So that kind of means nothing special happened here at all. You had a function, you applied another function, you applied another function, and they happen in that order. So that's kind of like no surprise, it's pure, nothing bad happened. Whereas the maybe monad is more like exception throwing. So you got just a computation, but then nothing happened, which means there was no good result, and all the computations that follow should just die. So what the maybe captures is an exception happened and the program was unable to recover. The state SA means that there's some state going on here, and let's say it's got a look state, which takes in some state, and then it produces, yes. A function like this, and then it's going to be a state SA. So what is state? It's a bit of a strange one, but it's saying I can sort of produce, if you give me some input S, I will be able to produce some output S together with a pure value of type A. So that's where we sort of store the state coming in and the store that comes out. The observation is that, so first of all, this is state for some S. You can think of this as being, so as imperative programmers, we normally think of the state as being a whole bunch of variables with all sorts of different names that you can acquire whenever you want, X, Y, Z, you like it. You're extending the state as you want. Here we're being a bit more analytical, and we're saying the whole of the state is S. You can't access any more than what I give you. So if I say you have one integer, you really have just one integer. You can't have 20 more, or whatever it is, it's just that single one. And so we don't even call it the integer X, we just say it's the integer you get when you ask get. It's the integer you put to when you say put. It's a single value. And when you use state in this way, what does putting to the state, and if you state this way, and you have a program that interacts with it in some way, you can imagine that you're doing a whole bunch of puts, a whole bunch of gets, some more puts and gets, etc., all into leave. Whatever program you write involving that state, you should be able to factor it into a single get followed by a single put. In other words, you get the initial state, you do whatever computation you like, and then you put the final state back in. And this is the idea that you get the initial state, you've done all sorts of crazy computation, and you put the final state back in. And that's what you get there. So no matter how many crazy puts and gets you have into leave, you will always factor back to this eventually. That's the kind of the insight that you want to have with this one. And then you might have something like the list monad, where you have empty lists, and then you have consing. So in Haskell, we would normally write this as the empty list, and we would normally write something like x cons x's as the list that we put together. And the idea with this monad is it's a bit like non-determinism. So the list of things that you have are all the potential answers that you might want to produce to your output. So I gave the example of square rooting earlier on. You want to put the positive and negative answers as two potential solutions to this thing. Or if you're generating a list of all the Pythagorean triples, so things where you've got a right angle between those two things, that's where you list all of the solutions in that space. So this monad is kind of like the monad that allows you to talk about non-deterministic multiple solutions. So each of these things, in a sense, capture different notions of computation, different ideas of what computation should do. So the first one was pure computations, nothing bad happens. The second one maybe was exceptions happen. The third one, state, is I interact with the state in some way. And the fourth one is I have non-deterministic computation. And what I talked about earlier on was these things called monad transformers, which are ways of composing these things together and sort of bolting on these additional abilities onto each other. But for now, we're just going to focus on individual monads by themselves in isolation, right? So, are there any questions about this, by the way? Because this is perhaps new to some. It will be trivial to those who've seen it before, but it might be quite weird to those who've not seen it before. Okay. I should have mentioned there is also the I/O monad, which I can't give you its definition without writing an entire compiler, right? So what does I/O do? Well, it interacts with whatever it is that your computer has access to, so maybe all POSIX or something. And I can't specify that, but the point is that it's the everything else monad that can do all sorts of cheeky things. Okay. So when we write monadic programs, we will often use the function called bind, which Joachim talked about earlier on today, which has the type MA to A to MB to MB. So you can see it as the impoverished version of fish that we heard earlier on, but actually they're interdefinable. So I'll just put the fish, B to MC. I'll put fish here just so you can see it. They're interdefinable, and the reason that bind is sort of the default version that we need to implement is because it kind of works better from the type perspective. Well, is that true? I'm not sure. I retract that completely. Sorry. It sort of works better when you compose things together. Sort of. I retract that as well. I don't know which one. So suppose you start off with some pure program P. The type of this is going to be MA, so it's got some monadic context with value A in it. And then we're going to bind it with some K, 1. So this would have, let's say, A to MB as its type. And then, I think this is why people like it, because you can do this. I still don't get it, because you can do it the other way. Anyway, I'm now muttering. B to MC, and then you can imagine having more and more Ks off to the right. And what we hope is that this is somehow associative, right? We should somehow think that, just as we saw with the fish, the associativity of bind should work out. Well, it does. So this whole computation here, because let's erase this thing here. So this computation here, if you have MA bind A to MB, well, MA bind A to MB gives you back something of type MB, so this thing has type MB. Now we've got an MB binding onto a B to MC, which means that this whole thing here better have type MC. So you can see that we can just tack in more continuations K to the right of this thing, and we'll keep on accumulating the results as we go. We talked about this idea of there being a kind of associativity to this. So what we want to do is we want to rewrite this as P bind something. So let's look at the types involved. This thing here has type MA. That means that whatever this is has type A2 MC. Because we know that the final result of this thing needs to be MC, like on the left-hand side. And if we're going to be using bind, then it better be of this type here. So how can we get an A to MC thing going on here? Well, the answer is we use a lambda, which binds a variable x of type A. And now we need to produce here something of type MC. So how can we possibly make something of type MC with all of these ingredients? Well, the only thing that I can do with this A is apply K1 to it. So I better apply K1 to it, and that gives me something of type NB. So if I do K1 applied to the X, now I've got something of type NB. I've got an NB, I've got a B to MC thing. How do I make an MC out of these? Well, the only thing I can do is bind K2. So I'm going to take this and bind K2. Okay? Now, this is super convoluted, right? And it's why I don't like this formulation of what bind does. And I think it's part of what might contribute to the infamy of the monads in Haskell, because you don't want to look at this. What you want to look at is the fish version of this that I showed you earlier, which is very obviously associative. If you squint, you can kind of see that it is associative, right? You've got this bracketing here on the left with the bind on the right-hand side, and here you've got the bind on the left-hand side with some other garbage going on in the middle. So it is recoverable as associative, but it's just not as clean. And this is all down to the actual interface being a bit funky. But hey. Any questions about this? Okay. So what I'll do now is I'll just demonstrate that the identity follows the associativity law, and then I'll do that with the other examples, and hopefully by the end of it all, our heads will be swimming and the time will be up. Okay? But at least you get a sense that all that's going on is some maths happened that showed you that those monads that we looked at, those containers of data, hold this sequentiality idea, and so it just means that computations are being pushed through. Okay, so the first one that I'll look at is going to be identity. So we want to define identity so I'm just looking at let's say equals. So what do I want to say here? I want to say something like make identity as type, give me an A, and I'll make you an identity of A. So the first thing I want to do is actually define what return does. So I probably said it too quickly earlier on, but return needs to respect fish properly. So that means that we need return to respect bind properly as well. And it's probably the easiest one to understand, so I should probably just give you the laws for that as well. So we want return to interact with bind in some way. Return has type A to MA. So it quite obviously could interact with it just by being the second parameter to this bind. So we can imagine that for any program P, bind return, what should that be equal to? So we need something of type MA, because the A's become the same. And we've got something of type MA, that's the P here. So P will do. So what we're saying is that returning the value that you've been given doesn't do anything magic. The other thing that you might want to do is I could start by having an MA here. So how can I make an MA out of return? Well, if I have a value type A, then return, let's call that X. So if this has type A, then this whole thing has type MA. Then I can bind that into some continuation K. Now this K has type A to MB. This whole thing has type MB because of the way bind works. And so we need here a value of type MB to be equal to this thing on the left-hand side. The only way you can manufacture something of type MB is through the K. So I need to pass that K the value of type A, which is X, so KX. What these two laws are telling you is that the way that return interacts with bind is pretty boring. You kind of get rid of the return in some way. So you can think of it as being like the unit of the monoid. In other words, It's the thing that just disappears when you compose it with the bind in some way, right? That'll become useful when we start looking at these identities. So how do we make an A to identity? So return x equals, so I need to make something of type identity A. The only constructor I've given you is this thing called muck identity, so I better muck identity x. I'm sort of aware that those of you who don't know Haskell are probably a little bit lost. I don't know how to get around that other than just like telling you. But do feel free to poke at me with questions if you're lost and you want to know more. I'm very happy to just slow down. All right. So let's talk about bind. So if we have identity with some x in it, bind some function f. Let's look at the, I should call that k, shouldn't I? So this thing here has type A, this thing here has type A to MB, but remember M is identity in this case, so it's identity B. And the whole computation should have type identity B. So how do I do that? Well, I've got this function that manufactures identity B's down here. It's called K. I've got the A that it needs. So this thing is just going to be equal to K applied to X. Now, I regret renaming my F to a K because if you read it as muck identity X bind F, we're just looking at function application of some weird function, right? And so, in a sense, the composition operation, as in the application function, is what bind is doing. It's just applying functions. So when we look at the associativity law that connects this up, what we should notice is that it just says something like application is associative, or function composition is associative, or something like that. Should I do that? Don't think I should. I can just say, trust me, it works. You go through the maths and it works out that this all ends up just being application, and then you notice application is associative, and then you go, oh yeah, well it is. And so that's why this ends up being like the monad for functions, right? Just applications and that sort of thing. Let's look at the maybe monad. So I said something like data maybe A, where there are two ways of constructing it. Either you can say nothing is a maybe of A, or just takes an A and produces a maybe A. Okay. I do want to remark on something actually, which is about identity, which is this. One thing that we do when we think about monads is we think about the language of things that could interact with this in other ways than just return, right? So what I mean is, what other things could you possibly do with a muck identity? With a muck identity, you're kind of stuck. There's not much more you can do. You can kind of like put things into it, and you get things out, and that's it. And so we call that sort of the algebra of identity is very, very limited. There's not much you can actually play with when you're there. When we look at the maybe monad in a second, we'll notice that there's one extra thing we can do with maybe that we can't do with identity. And so the algebra of maybe has just a bit more vocabulary to it, which we'll use. So let's look at return. So this has type A to maybe A. So what is return? So return takes in something of type X, and we need to make a maybe A out of this. I've told you there are two ways of making a maybe. It's either nothing or just something. If it's just something, you better give it an A. Oh well, I guess I'm going to give it just X as a possible way of implementing this, and that's that, right? So that's very, very boring. Now we implement bind. So I'll just write the type of bind down just to help you. Okay, so if we do this, then we have nothing, bind, let's say K. Okay, so we need to define nothing binds K to do something. So that means, so think of nothing as the computation that failed, and K is what we want to do after the computation has failed. So what we do, well, there's not much you can do, right? And if you follow the types, you realize that there's, your hand is forced as well. So we know that this thing here has type maybe A. This thing here has type A to maybe B. And on the right-hand side, we need to manufacture something of type maybe B. Where could that maybe B come from? Well, the only way to make a maybe B is applying K to an A. But I don't have any A's in my hands. So I'm utterly stuck. Except I'm not, because I could also manufacture a nothing which generates maybe A for any A I choose. I'll choose A to be B, so this is nothing that goes here. Note that the nothing on the left is not the same as the nothing on the right, because they have different types, but they both do nothing. And so this is like the propagation of error, right? So if you have an error on the left-hand side, everything to the right just disappears by proxy of this law, or this definition. Then we've got the version for just, so just x bind k. So this here has type A, this here has type A to maybe B, and then we're going to make it equal to something. Whatever this is better be of type maybe B, and then we're very limited in our options. We can only just pass in the x to the k, and we're done. Now, just some observations, right? This last clause should seem very familiar because actually we saw it on the previous slide, because basically it's the just take something of type A to maybe A, which is exactly the same signature as what this identity did. It took an A to the type that we're constructing. So they are basically synonyms for each other, and so it should be no surprise that they interact with bind in the same way. They just apply. So on reflection, that tells you that if you're in a just branch, just is going to behave just like function applications. In other words, purity is preserved in that branch. Everything is good. But if you see a nothing, then everything dies. And that's why you can think of the maybe monad as the failure monad. So we can think of having a fail operation that has type maybe A for all A's, where fail is equal to nothing. And this goes back to the reflection that I did earlier on about thinking about what the language of the monad is. Like, what other interactions can you have with this data type? And doing nothing is something that you can do here that you couldn't do before. So we think of ourselves as thinking, like, what are the operations that this could possibly mean? And failure is the natural operation that comes out of this. So now it's a good time to kind of go back to what you saw this morning about do notation, because I think it kind of, when I see these binds, if I program some fancy code, the reason I would ever use bind is because I want to somehow squeeze it all into one line so that I can publish a paper with one less line in my code, right? It's not because it's readable, it's not readable. And so, yeah.
Sorry, quick question. So you mentioned that for the maybe one and for the identity one, the bind operator is just a function applicator.
Correct.
Is it incorrect to say that this is it is the same for all the monads, just more bells and whistles, or if for other monads could it still be all just function application but with extra stuff?
No, not all of them actually. So things like state will be a bit more sophisticated than that, so we'll non-determinism. So yeah, these two happen to be a bit simple, but and it sort of makes sense, and it's a really good question. But the point here is that failure, in this sense, should be like the maybe monad is special because it's the minimal implementation of failure above, like on top of purity. So it's got just failure and do nothing and nothing else. So in that sense, we're trying to reduce it down to the story. Yeah, there's a more nuanced answer to your question, which is yes, even with state, if we pass in the state as being unit, as in the state with one value in it, then I think it could reduce to some kind of very dummy, everyone knows what the state is all the time, when you put and get to it, nothing happens, and so that reduces to just function application, I think. Let's elaborate later. So I think now's a good time to kind of just write some code, or at least understand what we did this morning. So when we write something like some program bind K1, bind K2, bind K3, this is obnoxious, right? We don't really want to write this. Because this K1 has type A to MB, this K2 has type B to MC, this one has type C to MD. I want to see the A's and the B's and the C's being passed around, right? And so what we can do is we can translate this, and Haskell does this with like pure syntactic sugar. It's not doing anything clever, it's just doing complete rewriting of this into something else, or the other way around. So we would write this as do, well, P has type MA, right? And so whenever you see something like P bind K, we're going to do nothing other than rewrite this as do, give me the X from P, and then continue with K on that X. So let's try and really understand this a bit more. This bind operation says it was between a P of type MA and a K of type A to MB. Well, a thing of type A to MB is just a function, right? So I could equivalently have written this as P bind lambda X to KX. Right, that's a bit of a strange way of writing it, because you would normally just not bother writing lambda X to KX, you just write K. But if I expand out that X, you get something like this. So you can view this as P occurred, and then whatever P did, it produced something. Let's call that something X, and let's pass that X on to K. Well, that's what I wrote down here. I said do something. P performed, bind it to X, and then do KX. So these two notations here should look pretty similar. We've basically just wrapped together a bind and a lambda into a do with some arrow, right? And so by process of expansion, this thing can be rewritten as something like, give me this from P, then give me, I don't know, Y1 from K1 applied to X, Y2 from K2 applied to Y1, Y3 from K3 applied to Y2, and then maybe I could even stick in a return here, and then some of you will say, Nick, you're cheating. You didn't tell me about the return before. That's very naughty. And the answer is, well, I kind of did actually already tell you about this, because I get you to know about how bind and return interact. And so actually I can rewrite my returns whenever I want to, and so here I'm doing exactly that. So this is kind of like why Haskell is my favorite imperative language, right? So, and also it's sort of tongue-in-cheek, the answer to do imperative languages have effects, and the answer is, yeah, this is an imperative language. And in fact, the whole Monad story was built around trying to build imperative features into this language. Yeah, I was once asked about, my group and its role as in functional programming, and I was like, well, my group doesn't do functional programming, we just do imperative programming in a functional language. So, okay, yeah.
Am I right in thinking that we're basically unpacking the monads to put stuff into the Y values?
Sorry, say that again.
Are we kind of unpacking the monads to put stuff into the Y values here?
Are we unpacking the monads to put things into the Y values?
To get the A that's inside the A.
Yeah, that is a good mental model to have, yes.
So how would this work then with like because like the list one can have more than one value here, so how does that work?
Yeah, great, good question. Yeah, so list seems really confusing because there are lots of lambdas going on. How can that be the case, right? And so what happens with the list monad is that each of those binds aren't actually binding a single variable. They're actually a for loop going through all of the variables, but naming each one in turn the same thing. So it's like a nested loop within a loop within a loop within a loop.
And this is syntactic sugar, so you could forget that you're doing it times.
Exactly. So the way that the syntactic sugar works is you write this code, and you can just read it as one of the results was produced by doing this series of y1, y2, y3, and then you carry on with the pure results. And then your mental model goes, but I'm in the list monad, which means each of those y1s, y2s, and y3s corresponds to one of the y's in that list. And then the whole thing kind of like, you go, oh yeah, okay, so I actually meant a very deeply nested iteration of things. Good question. Okay, anything else? So hopefully you get a feel for why that do notation is like sensible, because nobody wants to write this in their right mind. You want to write something like this instead. And the translation between the two is entirely syntactic. Sometimes if we want to sort of remove the variable, like, so you can imagine that maybe this y2 isn't used anywhere in the future code, in which case it's like an empty bind. So you can imagine that as a lambda, it would be something like lambda y2, but y2 is unused, why bother binding it? So we allow these things to be optional, in which case they can't appear anywhere in the future. And then that's how you kind of do this as syntactic sugar. So that allows you to just write single commands with no arrows to the left. It's basically saying the value that this returns back is useless, nobody's going to use it, so you can just do that. So there's again, it's a simple syntactic translation that does that. But it's all just syntactic sugar. Okay, which monad was next? I'm fearful to do state, because that one is a...
I think it was state next.
It was state next. Let's leave state to last. Let's practice on list first. So the return for list is like this. I'm going to use that notation for lists. So here we have a choice. We have lots of choices. We need to make a list of type A. What choices could I add here?
Either a or a singleton.
An empty list, a singleton list, any other contenders?
2x's,
2x's, 3x's, 4x's, and we keep going, right? So, so the reasonable answers we might think of would probably be no list, like an empty list, 1x, or maybe an infinitude of x's, right? Those would be three reasonable things to try and come up with. So how would we decide which ones? Well, the answer is the monad rules come to the rescue and give us some sort of way of navigating through this. There might be a way of thinking about streams as being infinite things, and are they monads, and we'd have to prove some laws about that as well, but let's not get into that territory. So intuitively, what return did before was it kind of didn't destroy any information. And we saw this already in the maybe monad. So what maybe did is returns just x, a single value. And what we saw fail doing was destroying data and doing nothing. And we proved that, you know, when you put the destroyer here, it kind of kills all the binders to the right. So it feels wrong to put the empty list as the return. Surely this law, there will be a law that fails somewhere. And indeed it will be like the left return law. So return x bind f will not preserve that value. We can look at that in a minute. But the point is that if we use the singleton value, then the return will work out just fine. So let's just do that. And then what we want to do now is bind. So bind has type, give me a list of A's. Okay. So if we have, we could do this by, let's just do this by pattern matching. So if we have the empty list coming in, bind some continuation k, what do we want to have happen? So this is our list of A's. This is our list. This is our function of type A to M to, sorry, A to list of B's. And here we want a list of B's. Well, I really haven't got any B's to play with at all. I haven't got any A's even, so all I can do is indeed just the empty list, right? That's going to be fairly easy. Otherwise, I've got something in the form x cons x's bind k. X has type A, x has type list of A, this has type A to MB. Sorry, A to list B. What do we want to do? We want to make a list of B's here, okay? And we want to make sure that everybody gets treated fairly. So our first guess is that we're probably going to make a B here using this A over here. So that means applying K to this thing. So that's this. That's giving me something of type list B. But I haven't done anything with my x's, and I feel a little bit sad. So how do I do something to these x's? I kind of wish that I could somehow transform all of these lists of a's into a list of b's. And if I could do that, then I could add it to this list of b's. And this is where we do that good old trick. We go, is there any function in the world that takes a list of a's and a function from a to list of b's and makes a list of b's with it? What could that function possibly be? And then I kind of noticed that this function takes a list of a's and a function and makes a list of b's. So maybe this is the function that I could use. And so I will use that function. So I can do x's bind k. That's my new list of b's. How do we smash two lists of b's together? Like that. Okay, so let's just try and understand this, because this is, if you have not seen this kind of trick before, it's a bit weird. We're recursively defining bind in terms of itself. Why is it okay? Because we're doing structural induction on the input list. So we've stripped off one value x, and then we're going to apply a k to that. And then now we know that this list x's is one smaller than the x cons x's we started with. And so when we do this thing, we know that this x's is one smaller than the thing we started with, which means that eventually this is going to hit the null case, and we're going to hit that, which means that we'll get the empty. That will look like an empty, and we're going to be appending all of the stuff we collected to the empty list, which is all the stuff we've had collected. So it all works out just fine. So the idea with this is we're kind of, in some sense, applying k to every single element inside the list. And going back to your question about monads and the bind notation, it feels a bit magic that we're dealing with one variable, but this is where the magic happened, right? The bind was actually not binding just the x, but binding all of the x's and hitting them with that k in sequence and going down. Yeah. Yeah. So Azalea's question is, what goes wrong if we if we said that return was empty list, I think, is that right?
Yeah.
Yeah. So what is, okay, so by definition it's this, but we wanted the law to be p bind return is equal to p for all p. Oh, that seems to be okay. It's not what I expected.
But it will always be as an output. Because return will just kill it and turn it into an output.
Sorry?
If we're on like what happens if return just spits out the empty list every time, right?
Yeah.
Well, that will just kill whatever output P has.
Yes. Oh yes. Oh yeah, we're talking about return being value, not the input list. Yeah, sorry. I was in completely wrong place. Let me translate that. So I saw some sharp faces. So we were discussing what happens if suppose that we're going to do suppose that return x equals this, right? Which would mean that p bind return is equal to p bind const this. Okay, so whatever is coming out of this bind, we're going to hit it with k. K is const unit, so we're always going to destroy all of the results. I think is probably the way I'd like to put it. Let's try it. Let's try it some more. Yeah, that's the function that was. Yeah, exactly. So we're going to just smash out everything. So this is not going to hold. It's not going to be p that we get back as the answer. Right. And I think we've got time to finish on state. Have we got time to? Yeah. So let's do state. So let's call it like state. And those of you who know Haskell will forgive me for not using new types. Okay, so the way that we can construct a state is by doing this. So let's look at what return does. So we need to make something of type state S. Okay, yeah. Oh, thank you. Thanks. So here we want to make something of type state SA. Okay, so we want to return x equals, and so the thing in here needs to be a state, and the only way I know to make a state is by using the book state function, so I'm going to use it. And so the thing in here needs to be of type S to SA. The only way I know to make something of type S to something, or X to or A something, or anything like that, is with a function. So I have to put in a function here. And so I'm going to make lambda, takes in the S, and what does it produce? So now the value in here has to be of type SA for this to work. So I'm going to make a pair. The first component has type S. I don't have many S's in hand except for the S I've been given. I don't have many A's in hand except for the X here of type A. So that's that. Okay. So let's just muse on what this has just said. It has said if you give me a state S, I'm going to output back that same state and the pure value X, and that's it. Right. So the state has not been modified. And you also need to remember what I said earlier about the way to read the state monad. It's a bit like all your sequence of do's and of gets and puts is equivalent to read the state once, do all your magic, put the state back again. And so that's what's going on here. We read the state once, put it back again. But this is value return when nothing bad happens. Okay, and now the hard case. So let's do signature again. So we've got a state SA to A to state SB to state SB. So just reading it, we're saying we've got a stateful program with some state S that returns a pure value type A. We've got a program that, if you give it a value type A, produces a stateful program still with the state S, but returns B instead. We want to make sure that these things kind of compose together. And internally, what you should be thinking is, here's a program with some state. Here's a program also with some state that might interact with some state. The output state of this better interact with the input state of this in some sense. And you want to rig them together. So what we're about to do is a bit of, Haskell kung fu to make sure that the state gets put into the right place, right? And it's not going to be pretty. So mux state. Okay. So what is a mux state? Well, it's this thing here. That is a function. I'm going to call it a program P of type S to SA. I can't unpack it more than that. It's not a lambda that's to construct these things. It's a function P of this form, right? So if you give P some state S, it will do some stuff with it. And I want to bind that into some kind of continuation K. So this has type A to state SB. Okay, so on the right-hand side, this better be something of type state SB. How do I construct something of type state? Well, I've only got one constructor, it's the muck. And this muck state takes in as its parameter this thing here, which is a function from type S to SA, which means it's a function of type S to SB. Sorry, S comma B in this case. All right, how am I going to feed it something of type S to SB? Well, I have to make a lambda because I don't have to make functions in any other way. So put it here, lambda S of type S. What's this value got to be? It's got to be something of type SB. All right, and now this is the point where we can make fun of ourselves for getting it wrong. So we need to output something of type S. Which S should I use? Oh, I've just got an S. Maybe I'll use that one. Maybe not. So to do so would be to entirely forget that P can also make S's. So we have two sources of S. We can either use the S we've just been given, or we could also use the S that P can manufacture, if only it were given an S as well. So we can imagine that somewhere we would have somewhere like let S prime equals, oh sorry, that's not what I want to say. I have an aversion to erasing. So we could imagine that if we had applied P to this input S, then we would get back out a new S and also something of type A. So we can say let S prime X equal P applied to S. So now we've got more decisions to make. We need to output something of type SB. Well, this has type S. What's the type of this X? It's of type A, okay. And it looks like we haven't even used K in all of this either, right? So we could also imagine doing something like K applied to, so let's put another letter over here. Like I said, it's going to be a bit messy. So we could imagine saying something like, let mux state, I don't know, Q equal the result of doing K applied to X, this X down here. So we can imagine that there's another clause that goes up here. If we had this X, we could apply K to it and get back a state, and the state has this type here, which means that we know it's going to function in it, which we call Q. So this has type S to SB, right? So what we want to return here is something of type SB. Which S should we pick, S or S prime? Now, if the philosophy is that what we're outputting is a pair, and the whole of this state PK is going to create a new state, state for computation, it's been given the initial state S. What's the final state that this should have? Well, it's the state after K has run. But the state after K has run is whatever Q is going to give us. Oh, have I got something wrong? No, I haven't got anything wrong. So we want to apply K to X. I feel like I've done something wrong. I feel like I want to say Q of S prime, but I don't think that's right.
If I can believe it or not, but is let mix state Q equal to the KX, so the mix state is applying to the Q?
Yeah, that's a sleight of hand that I should explain. So here I'm binding something to the result of KX, right? KX has type, so K, here has type A to state SB, so KX has type state SB. Right? Now, this value here, therefore, better have type state SB as well. There's only one way of making something of type state SB, that's having a mux state of something, and that something I'll call it Q. So that all type checks just fine, I think. But thanks for questioning it. What we could do is we could apply something like Q applied to S prime is going to give us something of type S double prime Y, right? And I've got the feeling that we're going to do something like this. But I don't trust myself enough to say that that's correct, and I'd have to just run it to find out. Like I said, this is always going to get messy. So the idea is that we're going to put our S in, we're going to apply our program P to it. Okay, so we get out a new state S prime, that's right, and then we also carry on with the program K. So we get that by applying K to X. We've got our Q coming out of this thing. We've got our new state, and our B comes out, which is our Y. I think that type checks, and I also think it's doing the right thing with the states. So we've got an state coming in, which is S. We've got an intermediate state, which is S prime, which is the one that gets fed through to K, and we've got the output state of K, which is the final S double prime. So there are three states, right? There's the initial state. So I'm now very convinced. So you can imagine that in this program up here, there's the state S coming in, and then whatever happens, the program key modified that state to make it S prime, and that state got fed through to the continuation K, ended up with an S prime prime. So we want the final state to be S prime prime. That's the state that we output here. And in terms of the value, there really was only one B, so I couldn't possibly have got that wrong, which is the Y that we got out. So so I think my confusion was that I was a bit worried that we would be outputting just S prime, but obviously that would completely neglect that K could also interact with the state, and so that would have been the wrong state to output as well. Okay. I think the terminating remark is the question that you asked earlier on about function applications. My intuition is if S was always units through all of this, we could vastly simplify the code and eventually it would look something like P applied, you apply K to the result of P or something like that, and nothing very much happens. But I'm not going to do that in 2 minutes.
Is it correct to think that it's function application while carrying the state through each of the applications?
Yes, yeah, that's right, exactly. And because the state in that case of unit is not interesting, it's just going to be a simple function application. Good, I think time's up. Thank you very much for listening. Hopefully that's demystified a little bit, and we'll have a good rest of school. Thanks.